Welcome to Quiet Universe, where the cosmos speaks in whispers, and we listen carefully. Today, we journey through the mysteries of the outer planets, where storms rage for centuries, moons hide oceans beneath icy surfaces, and rings slowly vanish into the darkness. These distant worlds, with their impossible winds, disappearing spots, and odd tilts, hold secrets that have puzzled astronomers for decades. From Jupiter's shrinking Great Red Spot to Neptune's elusive dark storms, we're about to explore a universe where the rules we know seem to bend and twist. So, sit back and join me as we dive into these mysteries, each one stranger than the last, and each begging the same question. What lies beneath the surface of these faraway worlds? In this journey, we're venturing into the furthest reaches of the solar system, where everything feels a little different, a little stranger. We'll unravel mysteries that have long captivated astronomers. Jupiter's Great Red Spot shrinking before our eyes, while its faint, unstable rings hang on the edge of existence. We'll question the extreme tilt of Uranus and the hypnotic hexagonal storm at Saturn's North Pole. Dive into the icy plumes of Enceladus, wondering if life lurks beneath its frozen surface, and follow Neptune's dark spots as they vanish and reappear without warning. We'll explore how these distant worlds defy expectations. Uranus and Neptune's puzzling heat discrepancies, the eerie methane lakes of Titan, the elusive Planet 9 hiding in the shadows, and Saturn's fading rings. Each phenomenon challenges our understanding of the solar system. From the erratic magnetic fields to the chaotic orbits of moons and Kuiper Belt objects, we'll ask deeper questions about the nature of these outer planets, their moons, and their influence over our solar neighborhood. Each mystery brings us closer to the unknown, each question propelling us further into the quiet darkness where these distant giants reside. Jupiter's Great Red Spot has long captured the imagination of scientists and space enthusiasts alike. It's this colossal storm, larger than Earth itself, swirling in Jupiter's atmosphere for centuries, and it's been a permanent fixture in our solar system's storytelling. The storm, which is essentially a giant anticyclonic disturbance, is an enigma. For a long time, it seemed invincible, an eternal mark on Jupiter's face. But recently, something unexpected has been happening. It's shrinking. This behemoth, once over 40,000 kilometers wide in the 19th century, has been steadily contracting. As of today, it's about half that size, measuring around 16,000 kilometers across. The very idea that something so monumental, so permanent in our collective understanding of the solar system, is shrinking makes you feel how small and fleeting even the grandest things in space can be. The Great Red Spot is, at its core, a storm like those on Earth, but on a scale we can barely comprehend. It's powered by Jupiter's chaotic atmosphere, where gases rise and fall, forming layers and bands of swirling clouds. This storm has managed to outlast any storm we've ever known, which is one of the mysteries that has baffled scientists for years. Most storms, even the largest hurricanes or cyclones on Earth, dissipate after a few weeks or months. But the Great Red Spot has been raging for at least 400 years, and potentially far longer. It raises the question, how does such a storm endure for so long? Theories abound. Some believe that the deeper layers of Jupiter's atmosphere, those we can't easily see, are feeding the storm, allowing it to persist. Others think that its persistence is due to the lack of solid ground on Jupiter. Storms on Earth die down because they eventually hit land, but Jupiter is a gas giant, so there's no surface for the storm to crash into. But while the storm has been an emblem of stability for centuries, scientists have been closely observing its slow but steady decline. In the past few decades, the edges of the Great Red Spot have started to erode. Little by little, it has become more circular and less elongated as its clouds are dragged away by other competing winds in Jupiter's atmosphere. You can almost picture this ancient storm being slowly torn apart, like threads unraveling from a once tightly wound tapestry. Yet, the shrinking of the Great Red Spot is not just a simple process of erosion. The storm also appears to be growing taller, almost as if it's being squeezed upwards as it contracts. Imagine a figure in a room that's slowly shrinking in on itself, forced to stand taller to avoid being crushed. That's what the Great Red Spot seems to be doing. Scientists suspect that this vertical stretching could be a way the storm is compensating for its loss of surface area, trying to maintain its strength even as it shrinks in diameter. The storm's iconic reddish color has also fluctuated over the years, sometimes fading, other times intensifying, which hints at complex chemical reactions in Jupiter's atmosphere that we still don't fully understand. The exact mechanisms of this color change remain another mystery tied to the Great Red Spot, but one thing is clear. It's alive in the sense that it's constantly evolving. There's a bittersweet feeling about the slow demise of the Great Red Spot. We've come to know it as a cosmic constant, an eternal maelstrom. But in a way, watching it shrink reminds us that nothing in space is truly eternal. Just as stars die, planets change, and galaxies evolve, this storm, too, is subject to the forces of time and change. And while we can predict that it will continue to exist for a while longer, there's a haunting question in the background. Will the Great Red Spot eventually disappear? Some researchers suggest it might fade away in the coming decades or centuries, a blink in cosmic time. What will Jupiter be like without its most iconic feature? Will another storm rise to take its place? Or will the planet's atmosphere shift into something entirely different, leaving behind nothing but the memory of this once mighty storm? Jupiter is constantly changing, and the Great Red Spot's shrinking fits into a broader narrative of an ever-evolving planet. The storm may seem ageless, but it too is caught in the dynamic flux of Jupiter's vast and complex atmosphere. The fact that we're witnessing this change, something that generations of astronomers only speculated about, feels like both a privilege and a reminder of our own fleeting place in the universe. What we're seeing now, this ancient storm shrinking and stretching, is a moment in time. In 100 years, or perhaps less, the Great Red Spot might be something entirely different, or it might be gone. We're observing a phenomenon in its twilight, like watching a mighty river slowly dry up after millennia of relentless flow. The shrinking of the Great Red Spot is not just a scientific curiosity. It's a story about how even the most immense and seemingly unstoppable forces in the universe are subject to change. It's a humbling reminder of the impermanence of everything, from the smallest human endeavor to the largest storm in the solar system. Watching the Great Red Spot shrink is like seeing the universe write its own history, knowing that even the most ancient features of the cosmos are destined to evolve, shrink, or fade away, leaving us to wonder what will fill the void they leave behind. Uranus stands out in the solar system, not because it's the farthest planet or the coldest, but because of something much stranger: its extreme axial tilt. Most planets spin like tops, with their poles pointing roughly up and down relative to the plane of their orbit. But Uranus? It rolls on its side, almost as if some invisible hand tipped it over. Its axis is tilted at an incredible 98 degrees, meaning that for a good portion of its orbit, one of its poles points directly at the sun. It's an oddity that has puzzled scientists for centuries, and even now, the full story behind this dramatic tilt remains a bit of a cosmic mystery. Imagine looking at the solar system from above. All the planets, more or less, spin in a consistent direction as they circle the sun, their poles standing upright in comparison to the orbital plane. But Uranus breaks all the rules. It's like the one rebel in a classroom where everyone else is behaving. The planet doesn't just spin differently, its whole orientation is wrong. For 42 years at a time, the poles take turns basking in continuous sunlight or plunging into complete darkness, which isn't something you see on Earth or anywhere else in the solar system. For half of its year, which takes 84 Earth years, one hemisphere is bathed in sunlight, while the other is in a perpetual night. This leads to bizarre seasonal changes that are almost impossible to compare to anything on our home planet. It's almost as if the planet has its own alien rhythm, moving to a tune that no one else can hear. So, what could possibly cause a planet to lie on its side like this? The most accepted theory is that, at some point in its ancient past, Uranus experienced a catastrophic collision with another celestial object, perhaps something the size of Earth, or even larger. This collision would have knocked it off its upright axis, sending it spinning into this sideways orientation. You can almost picture the scene billions of years ago, when some rogue planet or massive asteroid barreled through space and smashed into Uranus, forever changing its destiny. It's a dramatic idea that one event could permanently alter the course of a world's history, leaving it spinning differently from its planetary siblings. But there's more to the story than just the tilt. Uranus's moons and rings also orbit in this strange orientation, as if they too were affected by this colossal event. It's as if the whole system around Uranus was dragged into its odd spin, with everything caught in the aftermath of this ancient cosmic collision. The moons are locked into this tilted rotation, following the planet's odd dance around the sun. They, like Uranus, have no choice but to move in this strange, sideways path. Interestingly, Uranus's tilt creates seasons that are almost incomprehensible by Earth's standards. Imagine a planet where the sun stays directly overhead at the pole for 42 straight years, only to be followed by 42 years of darkness. In the mid-latitudes, the sun would rise and set in bizarre arcs, sometimes skimming along the horizon for decades. And in between these long summers and winters, the planet experiences brief periods where the equator gets some sunlight, but those times are fleeting. It's a slow, glacial kind of change, fitting for a planet so far from the sun. Seasons on Uranus don't come and go with the regularity of those on Earth, where we measure them in months. Here, it's a process that takes decades, with entire generations of life passing on Earth before a single year has even gone by on Uranus. What's even stranger is that despite this extreme tilt, Uranus doesn't have wild temperature swings. Its atmosphere remains uniformly cold, even at the poles where sunlight can shine continuously for decades. One would expect that one side of the planet would bake in the sun while the other froze, but that's not what happens. Uranus is uniformly freezing, sitting at temperatures around -224 degrees Celsius, one of the coldest places in the solar system. This uniform temperature, despite the extreme seasonal light shifts, only adds to the intrigue. Scientists believe this could be due to some deep atmospheric circulation patterns we don't fully understand yet. It's almost as if the planet is keeping secrets from us, hiding the full complexity of what's happening beneath its cloud tops. The mystery deepens when you look at Uranus's magnetic field, which, like the planet itself, is all out of whack. Unlike Earth's magnetic field, which is aligned with our rotational axis, Uranus's magnetic field is tilted and offset dramatically, as if someone tried to align it but gave up halfway through. It doesn't line up with the planet's poles, and it shifts unpredictably, further adding to the strangeness of this world. This chaotic magnetic field might be tied to its tilt, or it could be a result of something happening deep within the planet that we simply don't understand yet. Uranus's tilt also gives rise to other phenomena that are still under study. The planet's atmosphere is mostly made of hydrogen and helium, but it's the small percentage of methane that gives it that pale blue color. And while we have some understanding of what Uranus is made of, the details of its internal structure remain elusive. The planet's interior could contain massive amounts of water, ammonia, and methane, but we've never been able to probe it directly. That collision, if it happened, could have affected not only its spin but also its internal layers, possibly leading to the strange behavior we see today. In the end, Uranus's extreme axial tilt is a reminder of just how wild and unpredictable the cosmos can be. While we're used to thinking of planets as orderly, stable bodies moving in predictable paths, Uranus challenges that perception. Its sideways spin is a testament to the chaotic, sometimes violent nature of the universe, where planets can be knocked over, moons can be captured, and entire systems can be thrown into disarray. There's a strange beauty in the randomness of it all, in the idea that even planets as massive as Uranus aren't immune to the forces of chaos. It's a reminder that the universe is still full of mysteries, and even the planets we think we understand can surprise us in the most unexpected ways. Saturn, the planet known for its majestic rings, hides something equally strange and compelling at its north pole, a vast, hexagonal storm. It's a sight that seems too geometrically perfect for nature, something more likely to be found in an artist's rendering than on a distant gas giant. But this phenomenon is real, and it's one of the most puzzling weather patterns ever discovered in our solar system. Unlike the swirling, chaotic storms we're used to seeing on Earth or even the iconic Great Red Spot on Jupiter, this storm has sharp, defined edges. It forms a six-sided shape that's so precise it looks as though it was carved out by some unseen cosmic force. The sheer oddity of this storm raises countless questions. Why a hexagon? What forces could be at play in an atmosphere so alien to our understanding? The hexagon itself is massive, stretching about 30,000 kilometers across. That's large enough to fit almost 4 Earths inside of it. This isn't some passing weather pattern either. It's been there for decades, possibly centuries, locked in place like a strange permanent feature of Saturn's North Pole. When the Voyager spacecraft first captured images of it in the early 1980s, it was one of those moments that shook the scientific community. No one expected to see something so bizarre. And yet, there it was, spinning endlessly with its 6 perfect sides, rotating in sync with Saturn's long seasons. As our spacecraft got closer, with more detailed images from the Cassini mission in the 2000s, the mystery only deepened. Here was a structure in the clouds of a gas giant that defied conventional explanation. What's even more intriguing is that it's not just the storm itself, but the movement within it. Winds within the hexagon race at speeds of up to 300 kilometers per hour, faster than the strongest hurricanes on Earth. But unlike our storms, which are turbulent and messy, Saturn's hexagonal storm retains its shape as it spins. There's a kind of eerie stability to it. Imagine a whirlpool in the ocean that refuses to break apart, no matter how hard the waves crash around it. That's what this storm is like, almost unnaturally resilient. The winds swirl inside the hexagon, creating a pattern of smaller storms within the larger one, as though the entire system is caught in some strange cosmic dance. The geometry of the hexagon is what really captivates the imagination. Nature rarely creates such clean, straight lines, especially not in the chaotic environment of a gas giant's atmosphere. On Earth, storms are generally round or elliptical, their shapes dictated by the way winds move and interact with the surface. But Saturn doesn't have a solid surface, just layers of gas swirling around an unseen core. The hexagon doesn't seem to make sense within the framework of what we understand about planetary weather. Yet, there it is, defying explanation. One theory suggests that the hexagon is the result of a standing wave pattern in Saturn's atmosphere, where winds at different latitudes move at different speeds, creating this geometric boundary. But even that explanation feels incomplete, as if we're just scratching the surface of a much deeper, more complex mystery. And then there's the color. The storm isn't just notable for its shape. It changes color, too. When Cassini observed the hexagon during Saturn's long winter, it was a pale blue, a reflection of the frigid conditions at the pole. But as the planet's northern hemisphere tilted toward the sun and the seasons changed, the hexagon began to shift in hue, turning a golden yellow. This transformation is likely due to the increased sunlight breaking down the molecules in Saturn's upper atmosphere, allowing hazes to form. But there's something almost magical about watching a storm of this magnitude and shape change colors with the seasons. It gives the hexagon a strange, almost living quality, as if it's responding to the rhythms of Saturn's orbit. What adds to the surreal nature of the hexagon is that it seems so out of place. The rest of Saturn is a planet of rings, bands, and ovals. Its atmosphere is streaked with long, horizontal bands of clouds, driven by winds moving at different speeds across its surface. These bands are what we expect to see on a gas giant, with their fluid, ever-shifting boundaries. But the hexagon doesn't fit that mold. It's as if a sharp-edged figure had been cut into the soft, flowing fabric of Saturn's atmosphere. Even more bizarre is that there's no equivalent hexagon at Saturn's south pole. The southern hemisphere has its own storm, a massive vortex resembling a hurricane, but it's circular, not geometric. This asymmetry only deepens the mystery. Why would one pole have such a structured storm while the other does not? The sheer endurance of the hexagonal storm is another layer to its mystery. Unlike the storms on Earth that dissipate after a few weeks, or even the Great Red Spot on Jupiter, which is slowly shrinking, Saturn's hexagon shows no signs of breaking apart. It has likely existed for as long as we've been observing the planet, and possibly much longer. The consistency with which it holds its shape in such a chaotic environment is a testament to forces we don't yet fully comprehend. It's as if this storm operates under a different set of rules, immune to the turbulence that defines most planetary weather systems. Every time we learn something new about Saturn's hexagon, more questions seem to surface. How can a planet known for its rings, a symbol of harmony and balance, harbor something so anomalous at its pole? What does the hexagon tell us about the deeper workings of Saturn's atmosphere? About the way winds and gases interact on a planet that's so different from our own? The more we observe it, the more it feels like an alien riddle. A reminder that the solar system still holds secrets that we can't easily unravel. In a universe where so much feels random and chaotic, Saturn's hexagonal storm stands out not just for its beauty, but for its defiance of our expectations. It's a storm that shouldn't exist, but it does, spinning endlessly at the top of one of the most majestic planets in the solar system, inviting us to wonder at the forces that shaped it and the mysteries it still holds. Neptune is a planet of mystery, a distant, frozen world with winds faster than any hurricane on Earth. But what really draws attention are the strange, dark spots that appear and vanish on its surface without warning. These aren't like the stable, long-lived storms we see elsewhere in the solar system, such as Jupiter's Great Red Spot. Instead, Neptune's dark spots are transient, unpredictable, coming into existence for a short time before completely disappearing, as though the planet is playing some kind of cosmic sleight of hand. The most baffling part is how quickly they form and fade, leaving behind more questions than answers each time they vanish from view. The first of these spots was discovered in 1989 by the Voyager 2 spacecraft during its flyby of Neptune. Dubbed the Great Dark Spot, it seemed eerily familiar, almost like Jupiter's famous storm, but with key differences. This storm was dark, swirling in the planet's pale blue atmosphere, and yet it didn't stick around. In a blink, it was gone. By the time telescopes tried to find it a few years later, it had disappeared, leaving behind no trace of its existence. It's as though Neptune decided to erase the mark it had left on the world's collective imagination. This is a planet where nothing seems permanent, where storms rise and fall in the blink of a cosmic eye. Imagine standing on the surface, if such a thing were possible, of this far-off world, watching the deep blues of the planet's atmosphere as a dark spot begins to form. It's not slow or subtle. The storm swells quickly, a massive feature in the atmosphere that could swallow Earth whole. And just as suddenly, it's gone, as if Neptune decided to shrug off whatever was brewing beneath its clouds. It's almost haunting, the way these storms appear out of nowhere, like shadows rising from the depths of an ocean, then receding back into the cold, dark layers of Neptune's atmosphere. What drives the creation and destruction of these dark spots remains a puzzle. Scientists believe they are massive storm systems, similar in some ways to hurricanes on Earth, but vastly larger and more powerful. Yet, unlike Earth's storms, which are driven by the warmth of the planet's surface and the moisture in the air, Neptune's storms form in an atmosphere far colder and far less hospitable. The planet's atmosphere is made mostly of hydrogen, helium, and traces of methane, which gives it that striking blue color. But deep inside its clouds, powerful forces are at play, stirring up storms with enough energy to carve out these temporary dark spots. The energy driving these storms is likely coming from within Neptune itself, as the planet radiates more heat than it receives from the sun, though even this is shrouded in mystery. There's something strange about Neptune's weather, something that doesn't align with our understanding of how storms should work. The dark spots seem to arise without warning, like ghosts in the atmosphere, and then just as suddenly dissipate, as if they never existed. It's hard to pin down exactly what causes them to form. One moment the planet looks like a peaceful, calm sphere in the distant reaches of the solar system, and the next, one of these dark spots is swirling at its surface, as if Neptune has its own hidden turbulence beneath that serene blue exterior. You can almost imagine Neptune as a sleeping giant, its atmosphere quietly shifting until, suddenly, it stirs, unleashing these strange, temporary storms. The spots aren't uniform in their behavior either. Some are larger, some smaller, and some last longer than others, but they all seem to share that ephemeral quality. Even the most powerful telescopes struggle to catch these fleeting features, and when they do, the spots are often gone by the time we get a chance to observe them in detail. Neptune seems to be teasing us with these dark spots, giving just enough of a glimpse to remind us how little we really know about the outer reaches of our solar system. It's fascinating to think about the forces at work deep within Neptune's atmosphere that could lead to the rapid birth and death of these massive storms. These spots are likely formed by a mix of strong winds, atmospheric pressure, and internal heat that bubbles up from the planet's interior. But why do they form so quickly, and why do they disappear just as fast? Neptune is the windiest planet in the solar system, with gusts reaching speeds of over 1,500 kilometers per hour. These winds, far more powerful than anything we've ever experienced on Earth, could play a role in shaping and dispersing the dark spots. The atmosphere is a turbulent, swirling place, and it seems that at any moment, these dark storms could emerge from the chaos and vanish just as unpredictably. There's a kind of eerie beauty in the way these spots behave, like watching storm clouds gather on the horizon, only for the sky to clear before they ever reach you. Each time we catch a glimpse of one, it feels like a brief look into the hidden dynamics of a planet so far removed from our own experience. And each time one vanishes, it's a reminder that Neptune remains an enigma, a world full of storms and winds and mysteries that refuse to be easily solved. The dark spots also have a deeper layer of fascination because of how different Neptune is from Earth. On our planet, Storms come and go, but they follow patterns we've come to understand, driven by the interplay of heat, air, and water. Neptune's dark spots seem to follow rules of their own. They aren't shaped by oceans or land masses, or by seasonal changes like we experience. These storms rise up in an atmosphere that is mostly hydrogen and helium, with no solid surface beneath them, spinning in a world so far from the sun that sunlight is little more than a distant glimmer. It's a world that defies easy comparison, and its dark spots are just one example of the many puzzles that Neptune continues to present. In the end, Neptune's rapidly forming and disappearing dark spots are a stark reminder of how much there is left to learn about our own solar system. The more we study them, the more they challenge our understanding of weather, storm systems, and planetary atmospheres. We may catch fleeting glimpses of them, but Neptune holds its secrets close, making us work for every insight. These dark spots are a testament to the chaotic, shifting nature of Neptune itself, a world constantly in flux, always just beyond our reach. Uranus and Neptune are two ice giants that seem to defy logic, especially when it comes to their internal heat. On the surface, they appear similar. Bluish planets in the distant reaches of the solar system, both cold and composed of hydrogen, helium, and trace amounts of methane that give them their distinct color. But when you dig into what's happening beneath those icy clouds, things start to get weird. Neptune, despite being farther from the sun, emits about 2.6 times the energy it receives. It radiates a surprising amount of internal heat, hinting at some dynamic process happening deep within its atmosphere. Uranus, on the other hand, barely emits any more heat than it gets from the sun, as if the planet is holding something back, or simply missing that extra spark of energy that Neptune has. The discrepancy is striking. Neptune's internal heat gives it a livelier atmosphere, with active storms and high winds, while Uranus seems almost stagnant in comparison. This imbalance between the two planets is one of the great unsolved puzzles in planetary science. Why should two planets, nearly identical in size, composition, and distance from the sun, behave so differently? It's as if they are twins, but one is burning with hidden energy while the other is unervingly quiet. Scientists have been wrestling with this question for decades, trying to figure out what could cause such a stark difference between two planets that, on paper, should act similarly. One of the most perplexing things about Uranus is its extreme lack of heat. It's as though the planet has somehow locked away whatever warmth it once had, refusing to let it escape. Unlike Neptune, which appears to be radiating heat from its core, Uranus behaves like a planet that has been shut off from its own internal furnace. Theories abound as to why this might be. Some scientists suggest that a massive impact in Uranus's distant past, possibly the same event that knocked the planet onto its extreme tilt, could have disrupted its internal structure. This collision might have altered the way heat flows through the planet, trapping it deep within its core or dispersing it in ways we don't fully understand. If that's the case, Uranus could be sitting on a reservoir of internal heat, but it's locked away, inaccessible to the surface or atmosphere. Neptune, meanwhile, acts more like a typical gas giant, radiating heat into space from some unknown internal source. It's almost as if Neptune is still alive, dynamic and evolving, while Uranus remains frozen in time. Neptune's internal heat is likely generated by the slow contraction of the planet over time, a process that releases energy in the form of heat. It's a phenomenon known as Kelvin-Helmholtz contraction, and it's something we see in other gas giants like Jupiter and Saturn as well. But Uranus doesn't seem to be undergoing this process, or if it is, the heat isn't making it to the surface. It's a planetary paradox. Two planets so similar, yet behaving so differently. The difference in internal heat also affects their weather. Neptune's atmosphere is turbulent, with high-speed winds and massive storms that seem to bubble up from deep within the planet. The internal heat provides energy for these weather systems, driving the wild, chaotic conditions we see on Neptune. Uranus, in contrast, has an almost eerily calm atmosphere. Its storms are weaker, its winds slower. Without the extra boost of internal heat, the planet's weather seems to move in slow motion, like a storm that never quite reaches full force. The contrast is almost unsettling, like watching two siblings where one is always in motion while the other barely stirs. It's hard not to imagine these planets as characters in their own story, each with its own temperament. Neptune, the restless one, constantly changing, full of energy bubbling up from within. And Uranus, the quieter, more withdrawn sibling, keeping its secrets buried deep inside, as if unwilling to show its true self. But what is Uranus hiding? Why doesn't it let its heat out like Neptune does? These are the questions that keep scientists coming back, trying to unlock the mysteries of these distant worlds. There's also the possibility that something deeper is going on with Uranus that we just don't have the tools to detect yet. It could be that the planet's core is different in some fundamental way, maybe denser or more insulated than Neptune's, trapping the heat inside. Or perhaps there's some unknown process at work, something we haven't even considered, that's keeping Uranus in its strange state of thermal hibernation. Whatever the case, it's clear that these two planets are more than just cold, distant bodies drifting through space. They have their own unique internal dynamics, and understanding those could shed light on how planets form, evolve, and change over time. One of the most interesting ideas is that Uranus's cold nature might actually be a glimpse into the future of planets like Neptune. If Uranus's heat was locked away by a massive collision or some other cataclysmic event, could Neptune one day face a similar fate? Could the internal processes that are driving Neptune's heat eventually slow down or become disrupted, leaving it as cold and lifeless as Uranus? It's a chilling thought in more ways than one, and it makes the study of these two planets feel like a race against time to understand them before their internal dynamics change forever. What makes this all the more fascinating is how little we actually know. We've sent spacecraft to fly by these distant planets, but we've never explored them up close for an extended period. The data we have is limited, leaving us to fill in the gaps with theories and guesses. Yet the more we study them, the clearer it becomes that Uranus and Neptune are not just cold, distant worlds. They are active, complex systems with internal lives of their own. The heat discrepancies between them are a clue, a tantalizing hint that there is much more going on beneath the surface than we currently understand. In the end, it's hard not to feel a sense of wonder when thinking about Uranus and Neptune. These two ice giants, sitting at the farthest reaches of the solar system, are so familiar yet so different, each one carrying secrets that challenge our understanding of planetary science. The difference in their internal heat is just one piece of the puzzle, but it's a crucial one. A reminder that even in the coldest, most distant corners of our solar system, there's still warmth, energy, and mystery waiting to be uncovered. The thought of rings around a planet often conjures images of Saturn's magnificent and striking bands, but Jupiter, in its own quiet way, holds a far more fragile and elusive ring system. What is seen there isn't the grand spectacle of ice and rock that one might expect, but rather a delicate veil of dust, barely visible and constantly on the verge of being erased by the vast, turbulent forces that rule Jupiter's environment. It feels like a cosmic paradox. The largest planet in our solar system, capable of exerting unimaginable gravitational power, sustains something so faint, so ephemeral, that it seems almost out of place. It's as if these rings aren't meant to last, yet they persist, held together by a tenuous balance that defies the harsh reality surrounding them. These rings are born out of the smallest of celestial events, bits of dust thrown into space when tiny moons orbiting Jupiter are struck by meteoroids. Each collision sends a whisper of debris spiraling outward, only for it to be caught in the grasp of the giant's gravity. And there, the dust lingers, forming what we know as Jupiter's rings. But it's a fleeting existence for this material. Unlike the more stable and icy rings of Saturn, Jupiter's rings are subject to the relentless pull of the planet's magnetic field and the forces of radiation that emanate from the gas giant. These invisible hands constantly push and pull at the particles, making their orbits unstable, scattering them outward or pulling them back down toward the planet. As one tries to grasp the nature of these rings, it's hard not to see them as a reflection of something deeply human, fragile, transient, always on the edge of disappearing. Jupiter's rings don't command attention in the same way Saturn's do. They require patience, care, and a different kind of observation. Their beauty lies in their quiet persistence, in their ability to survive in the shadow of a planet that dwarfs them in every possible way. It's as if, in the vastness of space, these tiny particles still find a way to form something beautiful, despite the odds stacked against them. It feels like a reminder of how even in the most chaotic and destructive environments, something delicate can still exist, if only for a moment. The rings themselves are divided into different parts: the main ring, the halo, and the gossamer rings. The main ring is perhaps the easiest to identify, a slightly denser band formed from material thrown off by Jupiter's innermost moons, Metis and Adrastea. But even here, the dust particles are small, mere specks in the vastness of space. The gossamer rings, on the other hand, are so faint they seem almost like ghosts, trailing off from the moons Amalthea and Thebe. They extend far beyond the main ring, forming a diffuse, nearly invisible presence that can only be seen with the most sensitive instruments. It's a reminder of how much of the universe operates beyond our direct perception, how many things exist in a state of near invisibility, just out of reach. Despite their fragility, these rings are a testament to the dynamic processes that shape our solar system. They are constantly being reshaped, replenished by the impacts that occur in the space around Jupiter. In a way, they're always on the verge of disappearing, and yet they remain, a transient structure that may one day be entirely gone. To look at them is to look at something in flux, something that doesn't adhere to the usual notions of stability or permanence. For the human mind, there's a haunting resonance in observing something so unstable, yet so enduring in its own way. It's like watching sand blow across a desert, knowing each grain is moving, but together they create something momentarily whole. Jupiter's rings are a reminder that not everything grand has to be loud or dramatic. Some wonders in the universe are soft, barely there, holding on in spite of the forces that seem determined to tear them apart. And in that quiet defiance, there is something deeply human, an echo of our own persistence in a world that is often as unstable and unpredictable as the rings around a distant planet. On the surface of Titan, Saturn's largest moon, there is a landscape unlike anything found elsewhere in the solar system. Lakes of liquid methane and ethane cover parts of its frozen surface, eerily reminiscent of Earth's lakes and seas, but composed of something far stranger. The sight of them, from a distance, feels almost familiar. A shimmering expanse, quiet and still. But the knowledge that it isn't water changes everything. This liquid methane, an element that would be a gas under earthly conditions, flows and pools in Titan's frigid temperatures, creating an alien world where liquid hydrocarbons dominate. It feels like looking into a reflection of Earth, but one twisted by the extreme cold and distant location in the outer solar system. Yet what makes these lakes more than a mere curiosity is the mystery surrounding how they are replenished. Methane, under the conditions on Titan, shouldn't last long on the surface. Sunlight, what little of it reaches the distant moon, should break down methane over time. And yet, the lakes persist, seemingly fed by some unseen force, something deep beneath Titan's surface or perhaps high above in its thick, nitrogen-rich atmosphere. The steady, almost cyclical nature of this replenishment hints at processes we don't fully understand, and it gives Titan an air of mystery that's hard to shake. For a human observer, Titan's methane lakes feel like a reminder of how limited our understanding of the universe remains. Despite all our knowledge of planetary processes, Titan defies easy explanation. The idea of methane rains, forming from the thick clouds that swirl in the orange-hued skies, is a vision of weather so alien that it can't help but capture the imagination. The storms come and go, leaving behind traces of methane rivers that flow into the lakes, carving out valleys and shaping the terrain, not with water, but with a substance that we associate with fuel. And yet, there's something oddly poetic about it. This slow, rhythmic reshaping of Titan's surface, one drop of liquid methane at a time. Some scientists believe that these lakes are not merely surface features, but could be connected to underground reservoirs, where methane is stored and pushed back up through cryovolcanic activity or some other unseen force. The idea of Titan having its own hidden cycle, deep beneath the surface, speaks to the possibility of worlds that operate on principles so different from our own that they seem almost fictional. But as we study this distant moon, each discovery brings us closer to understanding not just Titan, but the diversity of processes that can shape planetary bodies across the cosmos. In another sense, these methane lakes feel like an enigma for us to unravel, something that pulls us back to the idea of exploration, of venturing into the unknown. Titan holds its secrets tightly, revealing them only in small fragments, and each new revelation leads to more questions. How exactly is methane being replenished at a rate that sustains these lakes? Is there something beneath the surface that fuels this cycle, or is it purely atmospheric? And if we could stand on the shores of one of these lakes, what would we feel? What would it mean to witness something so far removed from anything on Earth, yet so quietly similar? There's a subtle elegance in Titan's methane lakes, in their quiet defiance of what we expect a lake to be. And as we look deeper into the forces that sustain them, we are reminded of the limits of human knowledge, of how much more there is to discover in the universe. It feels like standing on the edge of a great unknown, knowing that beneath the surface, there's a world of complexity we can barely grasp. The replenishment of these lakes isn't just a scientific puzzle. It's a glimpse into the broader mysteries that Titan holds, and by extension, the mysteries that lie scattered throughout the cosmos, waiting for us to uncover them. In the early days of the solar system, the planets weren't in their current places, and the forces that shaped the order of things were chaotic, unpredictable, and violent. Jupiter, the largest of all planets, did not stay put in the outer reaches of the solar system as we see it today. Instead, it moved like a wandering giant, shifting closer to the Sun before pulling back out again. This journey, known as the Grand Tack hypothesis, suggests that Jupiter's early migration was a defining event that shaped the architecture of the solar system. It's an idea that feels both unsettling and awe-inspiring, as if the largest planet took a detour, exerting its influence over everything in its path, forever changing the orbits and destinies of the planets that would follow. As Jupiter drifted inward, it came perilously close to the region where the inner planets, including Earth, would eventually form. Its immense gravitational pull was like a wrecking ball, scattering planetesimals, the building blocks of planets, across vast distances, pulling some into the Sun and flinging others out into the void. For a moment, it's easy to imagine what that would have been like, as if the solar system was still deciding its fate, with the great giant moving closer to the Sun, reshaping the balance of power in those primordial days. Everything around it would have been in flux, and the gravitational waves it caused rippled through the early solar system, pushing and pulling at the surrounding debris. But this migration was not a simple journey inward. Something happened that caused Jupiter to change course. Perhaps it was the formation of Saturn, or perhaps some other unseen force in the disk of gas and dust that surrounded the young Sun. Whatever the cause, Jupiter began to retreat, reversing its path and moving back outward, like a ship tacking against the wind. This sudden shift meant that much of the material it had previously scattered was now left behind, allowing the inner planets, including Earth, to begin coalescing from the remains. It was as though Jupiter, having wreaked its havoc, withdrew, leaving enough material behind for the rocky planets to form. What's haunting about this idea is how close Jupiter came to preventing Earth from ever forming. If its inward journey had gone on just a little longer, the region of space where Earth now exists could have been completely cleared out, leaving nothing but the Sun and its massive companions, like Jupiter and Saturn. In some ways, it feels like a near miss, as if the very existence of our planet depended on this dance of gravity and timing, on the forces that caused Jupiter to change its mind and turn back. This migration also had a lasting impact on the outer solar system. As Jupiter moved outward again, it influenced the formation of the gas giants and the arrangement of the icy bodies in the Kuiper Belt. It was a process of destruction and creation, with Jupiter acting as both a disruptive force and a stabilizing one, shaping the future orbits of planets, moons, and asteroids. The solar system we see today is, in many ways, a result of this early period of instability, of a time when nothing was fixed and everything was in motion. For us, it's difficult to comprehend a world where the planets don't stay where they belong, where even the largest bodies in the solar system are free to roam. But Jupiter's migration is a reminder that the universe is far more dynamic than we often imagine, that the structures we see today are the result of eons of movement, of forces we can barely fathom. It's a humbling thought that the existence of Earth and the formation of the inner planets may have been the result of a giant planet's brief detour, a cosmic event that was both random and decisive. And it leaves us with the feeling that the history of the solar system is still written in the paths of its planets, in the scars of their migrations, and in the forces that, in the end, shaped everything we know. In the far reaches of the solar system, beyond the orbit of Neptune, there lies a region that has long intrigued astronomers. A place where the sun's light is faint and the cold stretches endlessly. For years, scientists have observed strange patterns in the orbits of distant objects, icy bodies that seem to move in ways that defy the pull of the known planets. These anomalies hint at something lurking out there, a distant and unseen force, perhaps a massive planet yet to be discovered. This idea, the possibility of a Planet 9, pulls at the imagination, offering a glimpse of something hidden, something that has eluded our view for so long. The thought of a planet so far from the Sun, yet so powerful that it influences the orbits of objects thousands of kilometers away, feels almost otherworldly. If Planet 9 exists, it would be a giant, a planet much larger than Earth, but its distance from the Sun would place it so far out that it might take tens of thousands of years to complete a single orbit. To us, it feels like trying to find a ghost. Its presence is inferred, its existence still debated, but there's something there, something causing the gravitational disturbances that ripple through the outer solar system. For the human mind, the search for Planet 9 is like chasing a shadow across the dark edges of space. We don't know exactly where it is or what it looks like, but every slight hint of its presence brings us closer to uncovering a hidden chapter in the story of the solar system. It feels as though there's a distant realm that we haven't yet explored, one that holds its secrets just beyond our reach, and with every new calculation, we inch closer to revealing it. The telescopes scan the sky, searching for that faint signal, for the sign that Planet 9 might be real, waiting in the cold dark. It's not just a quest for a planet. It's a quest to understand the solar system's past. If Planet 9 exists, it may be a relic of the early solar system, a planet that was thrown out to the farthest edges during the chaotic days when the gas giants shifted and migrated, much like Jupiter did. This planet, if it's there, could hold the key to understanding the strange gravitational forces that shape the distant objects in the Kuiper Belt, those icy worlds that orbit far beyond Neptune. Its presence would explain so much, and yet the more we search, the more elusive it seems to become, as if it's always just one step ahead of us, retreating into the darkness. For us on Earth, it's almost humbling to think that something so large, so influential, could exist in our own solar system and remain hidden for so long. The discovery of such a planet would shake our understanding of the solar system, showing us that even in the places we thought we knew, there are still vast unknowns waiting to be explored. It feels like a reminder that the universe is full of mysteries, even close to home, and that our knowledge is never as complete as we think. And yet, there's also a sense of wonder in this search. The idea that there could be a world out there, distant and cold, moving through the dark like a solitary traveler, carries a quiet allure. What kind of planet would it be? What forces shaped it? How did it come to exist so far from the warmth of the sun? And what secrets does it hold about the formation of our solar system? These questions linger in the minds of those who study the distant reaches of space, driving the search forward. The search for Planet 9 is, in many ways, a testament to the human spirit. The need to explore, to question, to reach beyond what we know. It's not just about finding a planet. It's about uncovering the unseen forces that shape our cosmic neighborhood, about pushing the boundaries of what we think is possible. And in that search, there's a reflection of our own curiosity, our own desire to understand the world and the universe around us, even if the answers lie millions of kilometers away, beyond the light of the sun. When you look at Saturn, the rings feel timeless, like they've been circling the planet forever. But their origin and age tell a story far more fleeting and mysterious. These shimmering bands of ice and rock seem to belong to a world that's always been majestic, yet recent studies have revealed that Saturn's rings may be much younger than the planet itself, perhaps only 100 to 200 million years old. In cosmic terms, this makes them a recent addition to the solar system, a late phenomenon in a universe billions of years old. The thought is almost unsettling, as if we are witnessing something ephemeral, a cosmic event that might one day vanish just as suddenly as it appeared. For scientists, the question of how these rings formed is deeply tied to their age. One prevailing idea is that they could be the remnants of a moon that ventured too close to Saturn, torn apart by the planet's immense gravity. The debris, scattered in orbit, flattened into the rings we see today. There's something profoundly tragic in that image. A moon pulled apart, unable to escape the pull of its parent planet, disintegrating into fragments that now swirl endlessly. It feels like a cosmic reminder of how fragile celestial bodies can be, how even something as massive as a moon can be shattered by the forces of gravity. Another theory suggests that the rings may have formed from the material left over from the formation of Saturn itself, a kind of cosmic dust that never quite coalesced into a moon or planet. If this is true, then the rings might have been around for a long time, but they have only recently become as prominent and bright as they are now. Perhaps the rings have always been there, quietly growing and evolving, until they reached their current state. a dazzling display of icy particles that catch the sunlight and reflect it back toward us. In either case, the idea that the rings might not be permanent, that they could eventually dissipate or fade, adds a sense of impermanence to something we've long considered a fixed part of the solar system. The particles that make up the rings are gradually falling towards Saturn, pulled by the planet's gravity, in a process that will one day strip the rings away completely. If you think about it, we live in a unique time where the rings are so visible and prominent, an era in Saturn's long history that may one day come to an end. For those who study Saturn, there's a delicate beauty in knowing that the rings are, in a sense, temporary. They are a reminder of the transient nature of cosmic phenomena, of how even the most striking features in the solar system can be fleeting. Saturn's rings may not last forever, but for now, they are a part of the planet's story, one that continues to unfold in the vastness of space. And as we gaze at them from Earth, we can't help but feel a connection to the broader processes that shape the universe. A reminder that even the most familiar objects in the night sky are subject to change, to forces beyond our control, shaping and reshaping the cosmos in ways we are only beginning to understand. In the icy depths of our solar system, Neptune drifts through space, its cold blue hue giving the impression of a world frozen in time. Yet, despite being so far from the Sun, Neptune radiates much more heat than it receives. This paradox has puzzled scientists for decades, as the planet seems to be holding on to a mysterious internal heat source, one that defies the logic of its distance from the Sun. When you imagine a planet as far out as Neptune, where sunlight is a weak and distant force, it's strange to think of it as warm at all, let alone warmer than expected. There's something about that hidden heat, lurking beneath its turbulent clouds, that draws you in, as if Neptune itself holds secrets about the nature of planets and the forces that govern them. The temperature anomaly is not a small one. Neptune emits about 2.6 times more energy than it receives from the Sun. And yet, scientists are still grasping at answers for what could be driving this excess heat. Some suggest that the planet's core, perhaps still cooling from its formation, is responsible for this output, releasing energy trapped since the early days of the solar system. If this is true, Neptune's internal heat could be a lingering echo from billions of years ago, when the solar system was a chaotic, swirling mass of dust and gas. There's something haunting in that idea, as if the planet is still carrying the heat of its birth, slowly releasing it into space. Other theories suggest more dynamic processes at work, involving the extreme atmospheric conditions on Neptune. The planet's winds, which are the fastest in the solar system, reaching speeds of up to 1,500 miles per hour, could play a role in transporting heat throughout the atmosphere, creating complex patterns that we have yet to fully understand. These violent winds, moving with unimaginable force, could be redistributing energy, feeding into the planet's internal warmth in ways we can't easily observe. Neptune, in this view, becomes more than a cold gas giant. It's a world driven by unseen forces, where energy moves in ways that elude easy explanation. There's also the possibility that we're dealing with unknown physics altogether, that Neptune's internal heat source may be something new, something that challenges our current understanding of planetary science. Perhaps it's a sign that gas giants like Neptune are more complex than we realized, with internal processes that don't fit neatly into our models. It's a humbling thought, one that reminds us of how much we still don't know about the planets in our own solar system, let alone the worlds beyond. For those who study Neptune, the planet's unexplained heat is a constant source of intrigue and frustration. It's as though Neptune is teasing us, revealing just enough to make us aware of its mysteries, but withholding the answers. And as our technology advances, allowing us to peer more deeply into the outer solar system, the mystery of Neptune's heat only deepens, as if the planet itself is defying our attempts to pin down its nature. There's a sense of awe that comes with knowing that even the coldest, most distant planets harbor their own forms of energy, that the universe is full of forces we are only beginning to grasp. Neptune's unexplained heat reminds us that, even in the coldest corners of space, warmth can exist in unexpected ways. It's a warmth that defies the vast distance from the Sun, a heat that suggests that the universe is more complex and alive with energy than we can easily imagine. And in that warmth, Neptune holds onto a mystery that continues to fascinate and challenge us, inviting us to keep searching for answers, even when they seem so far beyond our reach. Jupiter's polar auroras are unlike anything seen on Earth, not just in their size but in their intensity, their unrelenting brightness that pulses and swirls at the planet's poles. These brilliant displays of light, shimmering against the darkness of space, hold the key to understanding the deep, complex interactions between Jupiter and its environment. Unlike Earth's auroras, which are fueled by the solar wind, streams of charged particles from the Sun colliding with the Earth's magnetic field, Jupiter's auroras are born from a more mysterious and powerful process, one that's tied to the planet's immense magnetosphere and its unique relationship with its moons. At the heart of these dazzling light shows is the powerful magnetic field that surrounds Jupiter, the strongest of any planet in the solar system. It stretches far into space, capturing charged particles and funneling them toward the poles, where they smash into the upper atmosphere and ignite the gases, producing those glowing arcs of light. But it's not just the Sun's influence that drives these auroras. Jupiter's own volcanic moon, Io, plays an unexpected role. Io is constantly spewing volcanic material into space, sulfur, oxygen, and other elements, creating a plasma that gets trapped by Jupiter's magnetic field. The particles from Io's volcanic eruptions become part of a vast electric current that flows between the moon and the planet, intensifying the auroras in a way that feels almost otherworldly. It's fascinating to think of Io, a moon racked by volcanic eruptions, as the fuel source for these polar lights. The idea that a moon's volcanic outbursts, happening millions of kilometers away, could contribute to a planet's auroras feels both chaotic and harmonious. There's a strange dance between Jupiter and its moons, a constant exchange of energy that results in these bursts of light at the poles. The energy powering these auroras is immense, enough to light up a planet so massive that Earth could fit into it over 1,300 times. And yet, this energy creates something beautiful, something that moves with an ethereal grace through the Jovian skies. For us, watching these auroras from a distance, there's something deeply mesmerizing in knowing that these lights are the visible signs of powerful, invisible forces at work. It's a reminder that space, often thought of as a cold and empty void, is full of dynamic and unseen interactions. The magnetic field that governs these auroras, the constant bombardment of charged particles, and the contribution of Io's volcanic activity all come together in a spectacle that feels larger than life. In a way, it makes Jupiter feel more alive, as if the planet itself is breathing in these energetic pulses, casting its own light into the universe. Scientists who study Jupiter's auroras are constantly uncovering new details about how they work, but much remains a mystery. The sheer scale of these light shows is unlike anything we see on Earth, and the forces behind them are far more complex than those that drive our own auroras. The thought of standing beneath these polar lights, if such a thing were possible, is almost overwhelming. An experience that would make you feel the raw power of Jupiter, the vastness of its influence stretching far into the cosmos. Jupiter's polar auroras are not just a natural phenomenon. They are a reflection of the planet's unique place in the solar system, its immense size, and its magnetic strength. They serve as a reminder that even in the far reaches of space, far from our familiar Earth, the universe is full of beauty and mystery. And in the flickering light of those auroras, we catch a glimpse of the unseen forces that shape not just Jupiter, but the cosmos itself, leaving us in awe of the powerful and delicate balance that governs the planets and their interactions with the universe around them. Saturn's rings, which have long been a symbol of the planet's beauty and mystery, are slowly but surely slipping away. When you think of Saturn, those bright, icy bands circling the planet immediately come to mind, like a permanent fixture in the night sky. Yet, scientists have discovered that these iconic rings are vanishing at an alarming rate, being pulled into the planet by its gravitational field in a phenomenon that feels as inevitable as it is tragic. It's as though we are witnessing the slow, gradual disintegration of something that feels timeless, and the reality of their disappearance carries with it a quiet sense of loss. The process, often called ring rain, is surprisingly fast on a cosmic scale. Tiny particles of ice and rock, which make up the rings, are bombarded by the constant influence of Saturn's magnetic field. This causes them to become electrically charged, and these charged particles are then drawn toward the planet's upper atmosphere, where they burn up or dissolve. Imagine millions of small, icy particles falling from the rings like a slow, invisible rain, disappearing forever into the vast gas giant below. It's a process we can hardly see with our eyes, but one that's relentlessly shaping Saturn, quietly eroding the majestic rings. Estimates suggest that within the next 100 million years, the rings could be entirely gone. A blink of an eye in the long life of a planet. The thought of Saturn without its rings is unsettling, as though we are losing a piece of the universe that has always felt familiar and eternal. These rings, which may have formed relatively recently in cosmic terms, will disappear just as swiftly, leaving behind only faint memories of their existence. For now, we live in a unique time, one where we can witness these magnificent bands in their full glory, but the knowledge that future generations may never see them casts a shadow over their current beauty. There's something deeply human about this idea of witnessing a celestial body in the midst of a slow transformation. Saturn's rings, once thought of as a permanent feature, are instead revealed to be transient, fleeting. The universe, in its vastness, is not static, and even the most iconic features of a planet can fade away with time. This adds a layer of poignancy to every image we capture of Saturn and its rings, as though we are documenting not just a planet, but a fleeting moment in the life of the solar system. Scientists are still piecing together the exact timeline of how and why Saturn's rings formed, but what they know now is that the rings are much younger than Saturn itself. This means we are likely living through a rare window in the planet's history, one where the rings are present, bright, and visible. Their ultimate disappearance reminds us of the transient nature of all things, even those that seem the most stable and everlasting. As Saturn's rings continue to fade, they leave us with a sense of cosmic impermanence. The forces that govern their disappearance are constant, unyielding, and driven by the same laws of physics that shape the entire universe. And yet, in those last shimmering arcs of icy particles, there is a beauty that remains, a reminder of how, in the grand scope of the cosmos, even the most grandiose spectacles are only temporary, giving us all the more reason to marvel at them while they last. Triton, Neptune's largest moon, defies expectations from the very moment you consider its orbit. Unlike most moons in our solar system, which circle their planets in the same direction the planet rotates, Triton moves in the opposite direction. It's a retrograde orbit, one that suggests Triton wasn't always part of Neptune's family, but was instead an outsider, captured by the planet at some distant point in the past. There's something haunting about the idea of a moon that doesn't belong, one that was pulled into a gravitational embrace so powerful it couldn't escape. Triton's retrograde orbit is like a signature of this dramatic, violent past, a clue that its journey to becoming Neptune's moon wasn't smooth or ordinary. The capture theory suggests that Triton was once a body roaming the Kuiper Belt, a region beyond Neptune filled with icy remnants from the early solar system. Perhaps Triton was once part of a binary system, locked in a cosmic dance with another object until Neptune's powerful gravity disrupted that balance. The other object was flung away, and Triton became trapped in Neptune's gravity well, forced into its retrograde path. You can almost imagine the chaotic moment, the cosmic forces at play as Neptune took hold of this wandering body, turning what was once a free traveler into a captive, bound to orbit in defiance of all the other moons around it. Triton's capture wasn't a peaceful event. In fact, the process likely sent shockwaves through Neptune's existing system of moons, destabilizing or even ejecting some of the original moons from their orbits. What was once a settled system would have been thrown into chaos, as Triton's massive presence altered the gravitational balance. Over time, the orbits of Neptune's original moons would have shifted, with some being thrown out of the system entirely. In this way, Triton's story isn't just about its capture, but about the lasting effects it had on everything around it. It's a reminder that in the cosmos, nothing is static, and even a single event can reshape the entire landscape. There's also the matter of Triton's future. Because of its retrograde orbit, Triton is slowly spiraling closer to Neptune. One day, millions of years from now, it may collide with the planet or be torn apart by tidal forces, forming a new ring system around Neptune. The thought of Triton being torn apart by the same gravitational forces that captured it feels almost inevitable, like the final chapter in a long, complex relationship between moon and planet. Triton's retrograde orbit serves as a reminder of the forces that govern the universe, forces that can bind worlds together but also tear them apart, slowly and inexorably, over time. Triton itself is an intriguing world, one with an active geology, geysers that spout nitrogen gas, and a frozen surface that hints at a rich and complex history. It's a moon with character, one that seems out of place in its surroundings, and yet it's bound by the same cosmic forces that govern everything. Triton's retrograde orbit is just one piece of its mystery, but it speaks to the larger, untamed nature of space, where objects are constantly moving, shifting, and interacting in ways that are both chaotic and beautiful. In Triton's capture and its strange, backward orbit around Neptune, there's a sense of something unfinished, a story still unfolding. We look at this moon and see not just its present, but its past and future, all intertwined in the delicate balance of gravitational forces. It's a reminder that even in the farthest reaches of our solar system, the history of a single moon can tell a story of violence, beauty, and the complex dance of celestial bodies that continues even when we're not watching. Mars' atmosphere holds a mystery that has sparked imaginations and theories alike. Methane. This seemingly simple gas, when detected on a planet like Mars, opens a world of questions. On Earth, methane is predominantly a byproduct of life, produced by microbes or released from geological processes tied to organic activity. But on Mars, where life as we know it has never been confirmed, the periodic spikes in methane levels seem to tell a story that science has only begun to unravel. One of the more fascinating aspects of this story is the potential link between Mars' methane and the outer planets, a connection that feels almost improbable but is nonetheless steeped in scientific intrigue. Methane on Mars appears to rise and fall with the seasons, as if the planet is breathing, releasing pulses of the gas into its thin atmosphere. This cyclical appearance has raised the question of whether the methane is seeping up from underground reservoirs, stored for millennia in frozen pockets, or whether it's being generated by more active processes today. The idea that this methane could be tied to ancient events, possibly linked to the migration of icy bodies from the outer planets, offers an intriguing possibility. Mars, sitting on the edge of the asteroid belt, may have been bombarded by comets and other icy objects that originated in the far reaches of the solar system, bringing with them organic compounds and frozen methane. It's not hard to imagine a time when Mars, billions of years ago, was the target of countless impacts from these icy travelers. Some may have originated in the Kuiper Belt, a region beyond Neptune filled with remnants from the solar system's formation. These impacts could have delivered methane to Mars' surface, where it became trapped beneath layers of rock and ice. Over the eons, this methane could slowly escape, leaking into the atmosphere whenever the planet's shifting geology allowed it. In this scenario, the methane we see today is like a time capsule, a remnant of a time when Mars was bombarded by the same icy bodies that shaped the outer planets. But there's another possibility, one that ties Mars' methane to ongoing processes seen on the outer planets. On both Jupiter and Saturn, methane exists in abundance, not as a sign of life, but as a chemical byproduct of the planet's complex atmospheres. Could Mars be experiencing a much more subtle version of this, where its methane is produced by chemical reactions deep below the surface? Perhaps Mars, like the gas giants, has its own methane cycle, driven not by life but by geology, with methane being released as the planet undergoes seasonal temperature changes or seismic activity. Still, there's a haunting possibility that life, however small or simple, could be playing a role in the methane's presence. Some scientists have speculated that microbes, surviving deep underground where liquid water may still exist, could be producing methane as a metabolic byproduct. If these microbes exist, their connection to the methane production on Mars would draw a fascinating link to Earth, where similar microbes thrive in extreme environments. This would make Mars methane not just a mystery of geology, but a potential clue to an ancient biological connection, a fragile thread that could link the red planet to the same processes that sustain life on Earth. The mystery of Mars methane is a reminder of how complex and interconnected the solar system truly is. Whether the gas was delivered by icy bodies from the outer planets, or whether it's being produced by ongoing geological or even biological processes, it speaks to the shared history of planets and moons orbiting the Sun. Mars, in its dry, cold desolation, still holds traces of this ancient past, and its methane may be one of the last whispers of events that shaped not just the outer planets, but the entire solar system. As we continue to explore Mars, the question of where this methane comes from remains one of the most tantalizing mysteries, inviting us to look beyond the planet itself and into the deeper, more complex web of forces that have shaped it over time. The Kuiper Belt is a vast region at the edge of our solar system, beyond the orbit of Neptune, populated by icy bodies and dwarf planets like Pluto. It's a place where sunlight is faint and the cold is almost unimaginable. These objects, often remnants from the early days of our solar system's formation, move through this remote region in ways that are both mesmerizing and chaotic. Their orbits are unpredictable, shifting over millions or even billions of years. In the depths of space, far from the pull of the inner planets, the Kuiper Belt objects, KBOs, follow elliptical, tilted, and sometimes irregular orbits. The gravitational influence of Neptune is a major force, constantly tugging at these bodies, pulling them into patterns that can shift dramatically over time. Imagine a distant world where things are not as ordered and smooth as they seem on Earth. There's no certainty in their path. They don't follow neat, predictable tracks like the planets do. They are thrown off kilter by encounters, not just with Neptune, but with one another. Over time, these influences add up, nudging an object a little here, a little there. One day it's following a relatively calm trajectory, and over the course of millions of years, it may end up in an entirely different part of the solar system. It's like watching the subtle but relentless forces that wear down a mountain. The movement happens so slowly, it's almost imperceptible, but given enough time, dramatic shifts occur. There is something deeply human in the uncertainty of these orbits. These objects are travelers, wandering through space, shaped by forces beyond their control. They may get caught in resonances with Neptune, where for every 2 or 3 orbits they make, Neptune will make exactly one, keeping them locked in a kind of cosmic dance, always moving but never free. Others have more erratic paths, pushed into orbits that are far more elongated or inclined than their neighbors, sent hurtling farther from the Sun, perhaps only to be dragged back later. Their orbits may become so extreme that they are barely part of the Kuiper Belt anymore, but are instead flung out into the distant reaches of space, where the Sun is just another star in the sky. What complicates the situation further is the presence of hidden influences, the lingering suspicion of a yet undiscovered massive object, sometimes called Planet 9, lurking somewhere in the outer solar system. This hypothetical giant, far beyond Neptune, might be tugging at the KBOs in ways we don't fully understand. Some objects behave in ways that don't entirely fit the gravitational influence of known planets, suggesting the presence of this unseen body that distorts their paths even more. The gravitational field out there is a complex web, a delicate balance of forces, and these objects find themselves caught within it, twisting and shifting in their orbits as though they are being pulled by unseen threads. Humans can relate to the chaos of their journeys. Just as KBOs drift through the gravitational tides of the outer solar system, we too navigate forces that are often invisible to us. Emotions, memories, relationships, and decisions that set us on paths we don't always expect. Every so often, just like a Kuiper Belt object passing close to Neptune and feeling a sharp nudge, we experience moments that change our course. Sometimes it's a subtle redirection, sometimes a dramatic shift. Either way, the path we follow is rarely straight. It's an evolving dance with the universe, unpredictable yet beautiful in its complexity. Some KBOs are locked into relatively stable orbits, their paths regular enough that astronomers can predict their movements with reasonable confidence. Others, though, are more erratic, reflecting the tension between stability and chaos that defines much of the cosmos. The region is like the edge of a vast and ancient map, filled with known territories and blank spaces waiting to be explored. There's no telling exactly how these objects will evolve over eons, especially as unseen forces might alter their courses in ways we don't yet understand. But it's this unpredictability, this delicate interplay between order and chaos, that captures the imagination. The Kuiper Belt is a reminder of the complexity and beauty of the universe. Its chaotic orbits symbolize how even in the cold, distant reaches of space, things are constantly in motion, constantly evolving. Nothing is fixed or permanent. The vast forces that govern these icy objects are the same forces that shape everything, from galaxies to planets to human lives. We are all part of the same dynamic, interconnected universe, each of us following paths that are constantly being reshaped by forces seen and unseen. And in that way, we are not so different from those distant, wandering travelers at the edge of our solar system. Neptune's magnetic field is an enigma, a force that behaves unlike anything we experience here on Earth. It's not aligned with the planet's rotation like Earth's magnetic field, which is roughly centered and runs along our planet's axis. Instead, Neptune's magnetic field is tilted at a strange angle, about 47 degrees, an offset from the planet's core. It's as if the field has been pushed to the side, almost disjointed, floating away from where you might expect it to be. This quirkiness, this odd tilt, sets Neptune apart, making its magnetic field one of the most puzzling aspects of the planet. Imagine standing on Neptune, assuming you could survive its brutal winds and cold. You wouldn't feel the pull of a straightforward, predictable magnetic force. Instead, it would be erratic, unpredictable. The field seems to wander, as if the planet's magnetism is being guided by something less stable, something more volatile beneath its surface. Scientists believe this might be due to the structure of Neptune itself. Unlike Earth, where a molten iron core generates the magnetic field, Neptune may have an ocean of slushy, electrically conductive fluids like water and ammonia deep within. This turbulent, constantly moving interior could be responsible for the planet's shifting and unusual magnetism. It's as if Neptune's heart is restless, constantly in motion, churning up magnetic fields that refuse to align neatly. There's something deeply human about this mystery. Neptune's magnetic field is, in many ways, an embodiment of how life can feel. Often, we think things should be stable, that the forces guiding us should be clear and aligned. But sometimes, much like Neptune, we find ourselves pulled in unexpected directions, our internal compass thrown off, our stability challenged. Just as Neptune's field is offset, our own sense of direction can be knocked off course by internal forces we don't fully understand. Emotions, desires, conflicts that churn beneath the surface, influencing our choices in ways that aren't always obvious. Even the tilt of Neptune's magnetic field reflects this. It isn't just that the field is displaced, but it's also wildly misaligned with the planet's axis of rotation. This adds to the sense of unpredictability, as though Neptune itself is spinning one way, but its magnetic essence is heading off in a different direction. In a way, it's like those moments when we feel disconnected from our own intentions, when our actions don't quite line up with our desires, and we find ourselves behaving in ways that don't match the person we think we are. This strange magnetic behavior also hints at something deeper about the nature of the planet. Because the magnetic field is offset and tilted, it creates odd, uneven regions of strength across Neptune's surface. Some areas might experience a stronger pull, while others are left in magnetic quiet. It's a bit like the unevenness in our lives, the way some parts of our existence feel charged with energy, while others are calm or lacking. The dynamism, the imbalance, is what gives Neptune its character, just as the unevenness of our own lives gives us ours. And yet, despite all this unpredictability, there is a kind of order to it. Neptune's magnetic field is a product of the laws of physics, of forces acting in concert beneath the surface. The fluids swirling deep within the planet are interacting in ways that follow natural rules, even if we don't fully understand them yet. In the same way, our own internal chaos often has reasons behind it. Psychological, emotional, biological forces that guide us, even when they seem mysterious or disjointed. There's a deep connection between Neptune's unseen, turbulent interior and the way it manifests in the field we can observe from the outside. It's as if the planet itself is telling us that even the most chaotic-seeming forces have a source, a root cause. It's fascinating to think that, despite the vast distance between us and Neptune, and despite the planet's utterly alien conditions, we can still find a reflection of ourselves there. Neptune's tilted, offset magnetic field is a reminder that sometimes the things that seem most out of place, the forces that seem to pull us in odd directions, are still part of a larger system, a larger story. They are part of the way things are, and while they may seem strange, they are no less real or meaningful. The magnetic field of Neptune might not make sense at first glance, but it is part of the planet's identity, just as our own inner contradictions are part of ours. Uranus is a planet that defies expectations, a place where almost everything seems to break the rules. Its magnetic field is no exception. Unlike Earth, where the magnetic field is neatly aligned with the planet's axis of rotation, Uranus's magnetic field is chaotic and irregular. It's tilted at an angle of 60 degrees, and, even more strangely, it's not centered at all. It's significantly offset from the planet's core. This offset means that Uranus's magnetic field behaves in ways that are almost impossible to predict, twisting and turning as the planet rotates on its side, creating a wildly varying magnetic environment depending on where you are on the planet. The lines of magnetism that would normally provide a steady, uniform protective bubble are instead distorted, with some regions more exposed to the solar wind than others. Living on a world like Uranus would mean grappling with unpredictability at a fundamental level. The magnetic field doesn't protect the planet evenly. Sometimes it's strong and robust, but other times it's weak, allowing solar particles to pour in, interacting with the atmosphere and possibly fueling storms or auroras. It's like life when the safety net you rely on suddenly shifts or disappears, leaving you exposed to forces you hadn't anticipated. In Uranus's case, this means that different parts of the planet are subjected to intense bursts of solar wind at different times, creating a kind of cosmic weather that's far less stable than what we experience here on Earth. Adding to this is the unique rotation of Uranus. Unlike any other planet in the solar system, Uranus spins almost completely on its side. This means that as it orbits the Sun, its poles take turns pointing directly at the Sun, creating extreme seasons that last for decades. One pole can bake in sunlight for more than 20 years, while the other is plunged into an equally long night. This unusual tilt interacts with the planet's irregular magnetic field in ways that are still not fully understood, but the consequences are clear. Uranus experiences storms, huge, swirling tempests that seem to build during its long, strange seasons. Imagine being on a world where the seasons are not measured in months but in decades, where one part of your life might be lived in perpetual daylight and another in endless darkness. As the long seasons slowly shift, so too does the atmosphere of Uranus, with storms brewing as the poles take their turn facing the Sun. When sunlight finally reaches parts of the planet that have been in shadow for years, it triggers massive storms that sweep across the planet, fueled by the sudden influx of heat and energy. These storms are unpredictable, often appearing as giant, swirling systems of clouds that can stretch across thousands of kilometers. There's a certain poetry in how Uranus's seasons and storms seem to mirror the ebb and flow of life. There are times of calm, where everything seems to stand still, and then suddenly, without warning, a storm brews. A disruption, an upheaval, something that shakes the very foundations of the world you thought you knew. Just as the long winters of Uranus give way to unexpected bursts of atmospheric chaos, so too do we experience sudden, life-altering events after periods of quiet. The storms are reminders that nothing is ever as stable as it seems, that beneath the surface, forces are always building, waiting for their moment to be unleashed. What's striking about Uranus is that despite its distance from the Sun, despite the cold and isolation, it is still a place of dynamic change. The irregularity of its magnetic field and the long, slow seasons don't lead to stasis, but instead to periods of intense activity. This planet, which from afar might seem frozen and lifeless, is in fact home to tremendous forces at work beneath its surface. Its irregular magnetic field interacts with the Sun's energy in ways that we can only begin to understand, shaping the storms that sweep across its icy atmosphere. There is something profoundly human about this too. The idea that even in the coldest, most distant parts of our existence, there are still forces that shape and change us. Just as Uranus's storms are born from the slow accumulation of energy over decades, we too can go through long periods of calm, only to be thrown into chaos when the conditions are right. And yet, these storms aren't signs of destruction, but of life. They are part of the planet's natural cycle, just as our own upheavals are part of our growth. The irregular magnetic field, the strange tilt, the sudden storms, they all remind us that life, like the cosmos, is not a straight line. It bends, twists, and throws us into unexpected turbulence. And it is in this turbulence that we find the true energy of existence. Neptune's winds are something beyond comprehension, raging across the planet at speeds that surpass the sound barrier. These winds, the fastest in the solar system, can reach up to 1,200 miles per hour, about 2,000 kilometers per hour, far exceeding anything we've ever experienced on Earth. Imagine standing in the middle of a storm where the atmosphere itself is tearing past you faster than a jet plane. It's a place where the air moves with such incredible force that nothing could stand in its way. If you were there, the winds would rip through the sky with a kind of raw, terrifying power, one that feels almost alien. What makes these winds so extreme is the fact that Neptune is so far from the Sun, receiving only a fraction of the heat that reaches Earth. It might seem counterintuitive that a planet so distant, so cold, could have such violent winds. After all, on Earth, wind is largely driven by heat. The Sun warms the atmosphere, creating pressure differences that drive air to move. Yet on Neptune, The source of this energy remains a mystery. Scientists think it might have something to do with the planet's internal heat. Neptune emits more heat than it receives from the sun, and this internal energy could be fueling the fierce winds that rage across its atmosphere. It's as if the planet itself is restless, with forces beneath its icy clouds pushing the atmosphere into motion, creating storms and winds that defy the usual rules of planetary weather. There's a kind of beauty in the sheer scale of these winds. They sweep across a vast, featureless world, moving through an atmosphere of hydrogen, helium, and methane, carving through the clouds with unimaginable speed. It's like a constant state of chaos, where the forces of nature are unchecked and unyielding, where nothing can stay still for long. And yet, there's something eerily quiet about it too. Neptune's storms, for all their ferocity, take place in a near vacuum compared to Earth's atmosphere. The air is thin, and though the winds are incredibly fast, they wouldn't feel the same way they do in our dense atmosphere. It's a reminder that even when things seem out of control, they don't always play out in the ways we expect. In some ways, these winds reflect the idea of life moving at a pace that feels impossible to keep up with. There are times when everything seems to be rushing past, where the world feels like it's spinning out of control, and no matter how much you try to find solid ground, it keeps slipping away. On Neptune, this experience is taken to the extreme. The winds are relentless, and they never stop. It's a place where the very fabric of the atmosphere is in constant motion, where there's no escape from the chaos. But, like life, there's also a strange balance to it. Even in the middle of these supersonic winds, the planet itself continues to orbit the sun, following a predictable, steady path through space. The winds may be wild and ungovernable, but they are part of a larger system, a system that, on the grand scale, remains ordered and in control. The storms that form in Neptune's atmosphere, fueled by these winds, are enormous, dark patches that move across the planet, similar to Jupiter's Great Red Spot, but darker and more transient. These storms appear and disappear without warning, sometimes lasting for years, sometimes vanishing in a matter of months. The winds whip around them, creating swirling vortices that are as wide as Earth itself, and yet they are just temporary features on a planet that has been churning for billions of years. They come and go like moments of turmoil in our own lives. Intense, overwhelming, but fleeting in the grand scheme of things. What's particularly fascinating is how these winds and storms seem to be largely unaffected by the planet's distance from the sun. Neptune is so far away that the sun is little more than a distant star, and yet the planet is alive with motion. This raises questions about the very nature of weather and atmospheric dynamics, not just on Neptune, but everywhere. It suggests that there are forces at work that go beyond the simple equations we use to explain wind and storms on Earth. There's a deeper, more complex interaction of energy happening on Neptune, something we don't fully understand. It's a reminder that even the most familiar things, wind, weather, can take on forms that defy our expectations in the broader universe. Neptune's supersonic winds are a humbling example of the extremes that nature is capable of. They show us that even in the coldest, most distant corners of the solar system, there's still a fierce, unrelenting force at work. These winds don't follow the rules we've come to expect from our experience on Earth, just as life doesn't always unfold in the neat, predictable ways we hope. Instead, Neptune offers a glimpse of what happens when things are pushed to their limits, when the natural forces that govern the universe are allowed to run wild. It's a world where the boundaries of what's possible are stretched beyond anything we've imagined, where even the winds themselves defy the ordinary, creating a place that is both terrifying and awe-inspiring in its beauty. Europa, one of Jupiter's most intriguing moons, is covered in a shell of ice that stretches for miles. At first glance, it appears as a frozen, desolate world, but beneath this icy exterior, there's a sense of profound mystery and, perhaps, life itself. Europa's surface isn't just a simple layer of frozen water. It's a fractured, dynamic landscape of ice, shaped by forces deep beneath it. The ice is crisscrossed with dark streaks, ridges, and cracks, a kind of frozen jigsaw puzzle that tells a story of shifting, flexing, and even possibly of an ocean that lies hidden below. The ice on Europa is composed mostly of water, similar to the ice we find on Earth. But it's not the kind of still, unmoving ice you might find in Antarctica. Europa's surface is constantly being reshaped, not by the slow hand of weather or the sun, but by the immense gravitational pull of Jupiter. As Europa orbits its massive parent planet, Jupiter's gravity tugs at it, stretching and squeezing the moon in a process known as tidal flexing. This creates heat deep within Europa, enough to keep an entire subsurface ocean in a liquid state. The ice above this ocean cracks and shifts, creating the ridged, scarred surface we see today. In a way, the ice on Europa is like the skin of something alive, constantly responding to forces it can't escape. What's captivating about Europa's ice is not just its composition, but what it suggests about the moon's history and its potential for life. The surface is incredibly smooth compared to other celestial bodies, which means it's relatively young. Geologically speaking, only about 40 to 90 million years old. This implies that something is constantly renewing the ice, perhaps from eruptions of water or slush from the subsurface ocean below. These geysers could be depositing fresh layers of ice, covering older surfaces with new material, hiding what once was and creating an ever-changing environment. In this way, Europa's ice is not a passive barrier, but an active part of the moon's story, shaping and reshaping the landscape over time. There's something profoundly human in the idea of Europa's ice, with its layers that both reveal and conceal. Beneath that cold, seemingly impenetrable shell lies the possibility of an ocean that could harbor life. The ice is a boundary, both protecting what lies beneath and trapping it, much like the emotional walls people build around themselves. We create barriers to keep things safe, to keep them hidden, and yet, there's always something stirring beneath, some deeper current that pushes against the surface, occasionally breaking through in cracks and fissures. Europa's ice feels like a reflection of that duality, the need for protection and the unstoppable forces that demand change. The origin of Europa's ice surface goes back to the early days of the solar system. Like many of the moons of the gas giants, Europa likely formed from the leftover material that didn't coalesce into the planets. It was a time of chaos, where collisions and gravitational forces sculpted worlds in ways that still leave their mark today. Water ice, which is common in the outer solar system, became the defining feature of Europa. Over billions of years, the moon's surface has been shaped by both external impacts and internal forces. Comets and meteoroids have struck the surface, leaving craters that have mostly been erased by the resurfacing processes driven by the hidden ocean. It's as though Europa's surface is constantly wiping away the scars of the past, leaving only hints of the violence that created it. The cracks and ridges on Europa's surface, dark with material from beneath the ice, are a direct connection to that subsurface ocean. They suggest that the ice isn't completely solid all the way through. There are places where water or slushy material seeps up, freezing again as it reaches the cold surface. These ridges, known as lineae, are like scars, recording the moon's internal struggles. The presence of salts and other compounds on the surface, possibly brought up from the ocean below, adds another layer of complexity. These materials hint that the ocean is more than just water. It could be a briny, mineral-rich sea, potentially habitable for life as we know it. Europa's ice is also a frontier. Scientists are drawn to it because of what it represents, the closest place in our solar system where life might exist beyond Earth. If there are hydrothermal vents on the ocean floor, much like the ones on Earth, where life thrives in complete darkness, there could be ecosystems hidden under miles of ice. The ice, with its shifting, restless nature, becomes a barrier we long to cross, a wall that both hides and protects what might be one of the most profound discoveries in human history. Europa, with its cracked and scarred ice surface, is a reminder of the dynamic and often violent forces that shape worlds, both from within and without. Its ice tells a story of pressure, heat, and time, of a hidden ocean pressing up against a cold and fragile shell. It is a world where the simplest of materials, water, has become something extraordinary, a frozen surface that conceals unimaginable depths. And in those depths, beneath the fractured ice, lies the potential for something more. A hint that even in the most distant, most unlikely places, life may find a way to persist. Uranus's rings are a delicate, almost ethereal feature that quietly circles the planet, faint and elusive. Unlike the majestic and brightly visible rings of Saturn, Uranus's rings are dark and subtle, made up of narrow bands of particles that are hard to see unless you're looking at them under just the right light. It's as if they're trying to keep a low profile, existing in the background without drawing too much attention, yet they hold a mystery of their own. The rings are composed of dust and small, dark particles, possibly made of water ice mixed with something that darkens them, organic compounds, or radiation-processed material that has given them their almost invisible appearance. They don't reflect much sunlight, making them easy to overlook, but their existence is a clue to the planet's history. The formation of these rings wasn't something that scientists expected to find when Uranus was first explored. The idea of faint rings around a planet that is so distant from the Sun, a world tilted on its side, seemed surprising. Rings are typically thought of as the aftermath of collisions or the remnants of moons that were torn apart by a planet's gravity. And in Uranus's case, that might be exactly what happened. Moons or debris that once orbited the planet could have been pulled apart by the immense gravitational forces, especially since Uranus has a dramatic tilt that might create unusual tidal stresses on its surrounding objects. These rings, narrow and tightly confined, suggest that something violent happened in Uranus's past. The material in the rings could be the remnants of ancient moons that were shattered into pieces, either by collisions with comets or asteroids, or by being pulled apart by the gravity of the planet itself. Imagine moons that once orbited Uranus peacefully, their own small worlds, suddenly caught in a destructive dance with the planet. Over time, these moons might have been broken apart, reduced to rubble that now drifts around the planet in these faint, dark bands. It's like the remnants of a forgotten past, still circling the planet, hinting at something larger that once was. The dark, carbon-rich nature of the rings adds to their mysterious origins. While Saturn's rings are bright because they are made of relatively pure water ice, Uranus's rings are darker, suggesting they've been exposed to radiation or that they've been contaminated by other materials over time. Perhaps they've been bombarded by micrometeoroids, or maybe the radiation from the distant sun and cosmic rays has slowly altered their composition. It's a kind of quiet erosion that's taken place over millions or billions of years, slowly darkening the rings until they blend almost seamlessly into the backdrop of space. What's fascinating is the idea that these rings might not be permanent. Just as they were likely formed from the breakup of moons or material that couldn't hold together in Uranus's orbit, they might one day fade away entirely. The particles that make up the rings are small, and over time, they could be pulled down into the planet or blown away by the solar wind. The rings are fragile, temporary things, more like ghosts of the past than enduring features of the planet. And yet, in their fragility, they tell a powerful story about the processes that have shaped Uranus and its moons. The unexpected formation of these rings also raises questions about the evolution of the Uranian system. Uranus's tilt, which is extreme compared to other planets, might have come from a giant impact early in its history, a catastrophic event that knocked the planet on its side. This same impact could have set the stage for the formation of the rings, disrupting the orbits of moons or debris in the planet's gravitational field. In this way, the rings are a reminder of how chaotic the solar system's history has been, how planets and moons are shaped not just by slow, gradual processes, but by sudden, violent events that can leave their marks for billions of years. There's something deeply human in the fragility and transience of these rings. They are a product of destruction, of loss, but they continue to exist in a way that's both subtle and resilient. Just as we carry the marks of our own pasts, events that have shaped us, even if they're not immediately visible. Uranus's rings carry the legacy of moons that no longer exist, of collisions that happened eons ago. They're a reminder that even in the vastness of space, things are not as permanent as they seem. The rings, so faint and easy to overlook, are a testament to the idea that even the quietest, most unassuming features can hold the deepest stories. And yet, there's also something hopeful about them. Despite being born from destruction, they continue to circle the planet, holding on, enduring in their own way. They are part of a dynamic system, shaped by the forces of gravity and time, but still a feature of Uranus's unique world. It's as if they represent the idea that even in the aftermath of chaos, something can still remain. Something beautiful, if not entirely visible, still orbiting, still moving, still part of the larger story of the universe. Triton, Neptune's largest moon, is a place where the usual rules of geology are flipped upside down. Far from the molten lava and fiery eruptions we associate with volcanic activity, Triton experiences cryovolcanism, volcanoes that erupt not with molten rock, but with water, ammonia, and methane, substances that are frozen solid on Earth but behave like lava on this distant moon. Cryovolcanism on Triton is driven by something much colder, much quieter, but no less dramatic. It's a world where ice behaves like liquid, and the eruptions spew forth plumes of icy material instead of ash and magma. The idea that Triton, a moon so far from the warmth of the sun, can experience volcanic activity is astonishing. Cryovolcanism suggests that there is still internal heat within Triton, enough to melt subsurface materials and cause them to erupt to the surface. It's a place where ice becomes fluid under the right conditions, where ammonia or methane, which would be frozen solid here on Earth, is heated just enough by internal processes to break free from below the surface, gushing out into the frozen air. The material freezes almost immediately upon reaching the surface, creating bizarre landscapes of frost, ridges, and frozen plains, features that look otherworldly, even for a moon that already seems to defy expectations. The cryovolcanoes of Triton are not like the violent eruptions we see on Earth, with fire and destruction. Instead, these eruptions are more like fountains, slowly pushing up icy material that gently coats the surface. But just because it's quieter doesn't mean it's any less powerful. Triton's cryovolcanism tells us that there are forces at work deep beneath the surface, hidden from view, but shaping the moon in ways that are subtle and profound. There may be pockets of liquid water or slushy ammonia deep beneath Triton's icy crust, heated by the moon's internal processes, perhaps driven by tidal forces from Neptune's gravitational pull. As Triton orbits its distant parent planet, the constant tug and pull create friction deep within, generating enough heat to drive these strange, cold eruptions. Imagine standing on Triton's surface, surrounded by frozen plains under a pale, distant sun. Suddenly, from a fissure in the ground, a geyser of icy material erupts, not with the heat and violence of earthly volcanoes, but with an eerie calm, spewing forth plumes of nitrogen or water vapor that instantly freeze and fall back to the ground like snow. It's a quiet, cold eruption that feels almost peaceful, but it's a reminder that even in the coldest, most remote parts of the solar system, there are still forces bubbling beneath the surface, reshaping the landscape in ways that we are only beginning to understand. The presence of cryovolcanism on Triton also raises the possibility that there might be liquid water below its surface, perhaps even an ocean trapped beneath its frozen crust. And with that possibility comes the question of life. Could there be some form of life, hidden in the dark, cold depths of Triton's interior, surviving off the heat from its internal processes? We don't know, but cryovolcanism suggests that Triton is far from a dead world. It's active, dynamic, and evolving, its surface being constantly renewed by these cold eruptions that have been happening for millions of years. Cryovolcanism on Triton speaks to the strange beauty of the outer solar system, where nothing is quite as it seems. It's a place where ice can flow like water, where volcanoes are cold, and where even the most distant, seemingly lifeless moons have secrets beneath their surfaces. Triton's cryovolcanism is a reminder that life and activity in the universe can take forms that are utterly foreign to us, but no less real. It's a moon that defies easy classification, part frozen wasteland, part volcanic landscape, and in doing so, it challenges our understanding of what's possible. This quiet yet powerful process is a metaphor for the hidden depths that exist not only in moons like Triton, but within ourselves. Just as Triton's cryovolcanoes erupt from deep within, revealing that there is still heat, still movement, and still energy even in the coldest of places, we too have inner forces, often unseen, that shape us in ways that might not be immediately visible. There are eruptions of emotion, change, and growth that come not from external heat or pressure, but from something deep within that is constantly at work, quietly transforming who we are. Triton, with its cryovolcanic activity, shows us that even in the most distant and isolated places, there is still a pulse, still a beating heart. It's a moon that refuses to be frozen in time, constantly remaking itself through these strange, cold eruptions. And in that constant remaking, we find a kind of resilience, a reminder that even in the harshest environments, there is the potential for renewal, for activity, for life. Cryovolcanism on Triton is a quiet revolution, a slow but steady process that keeps this distant moon alive, and in doing so, it teaches us something about the endurance of the forces that shape the cosmos. Saturn's rings are one of the most striking sights in the solar system, a vast expanse of icy particles that orbit the planet like a cosmic masterpiece. But the structure of these rings isn't just a random arrangement of particles floating aimlessly in space. Beneath their beauty lies a complex system of order, one that owes its stability and form to a group of small, often overlooked moons known as shepherd moons. These moons play a quiet but crucial role in shaping and maintaining the intricate structure of Saturn's rings, almost as if they are the caretakers of this grand celestial architecture. Without them, the rings might not have the form we so admire today. They might drift apart or lose the sharp, defined edges that make them so captivating. The shepherd moons get their name because they herd the particles within Saturn's rings, using their gravity to keep them in place, to nudge them back into line whenever they start to wander. Imagine a flock of sheep scattered across a field, and a shepherd moving along the edges, guiding them, keeping them together so that they don't stray too far. This is essentially what these moons do, though instead of sheep, they are guiding billions of ice and rock particles that make up Saturn's rings. Their orbits are incredibly precise, and as they move through or near the rings, their gravity pulls on the ring particles, confining them into narrow bands and sharp edges, keeping them from spreading out too much or collapsing inward. It's not something you can see easily, but if you look closely at the gaps between the rings or the defined edges, you'll find the work of these shepherd moons. One of the most famous examples is the moon Prometheus, which patrols the narrow F-ring of Saturn. Prometheus tugs on the ring material as it moves along its orbit, creating streamers and waves that ripple through the ring. You can almost feel the tension between the moon and the ring particles, as if Prometheus is pulling the rings into place, keeping them in line, yet never too forcefully. It's a delicate balance, like someone gently pushing a swing at just the right time to keep it moving. These moons don't work alone, either. There are multiple shepherd moons interacting with different parts of Saturn's rings, each playing its part in this larger cosmic dance. Pandora, another small moon, works in tandem with Prometheus, on the opposite side of the F-ring, creating a dynamic where the ring is pushed and pulled from both directions. It's an elegant, almost invisible partnership between these moons and the rings, where gravity becomes the thread that holds everything together. If you didn't know they were there, you might think the rings were simply self-sustaining, but in reality, it's this network of shepherd moons that keep the rings in their iconic shapes. The mystery of how exactly these moons came to be in such precise orbits is still something that intrigues scientists. Did the moons form from the same material that makes up the rings? Or were they captured by Saturn's gravity long after the rings formed? It's possible that these moons are remnants of larger objects that once orbited Saturn but were broken apart by collisions or by Saturn's intense gravity, leaving behind smaller fragments that now serve as the shepherds of the rings. In this way, the shepherd moons might be survivors of a more violent past, continuing to serve a vital role in maintaining the structure that arose from the chaos that once surrounded Saturn. There's something deeply fascinating about the way these small, seemingly insignificant moons hold together such a vast and complex system. They're tiny in comparison to Saturn or even its larger moons, but their impact is monumental. It's a reminder that in the universe, size doesn't always equate to influence. These shepherd moons, small and often unnoticed, are what keep Saturn's rings from unraveling, from dissolving into disorder. It's like finding out that the quietest person in the room is the one holding everything together, the one making sure that the beautiful facade remains intact. In a sense, these shepherd moons are like the unsung heroes of Saturn's ring system. They go about their work silently, persistently, without any of the grandeur or attention that the rings themselves attract. And yet, without them, the rings wouldn't be the awe-inspiring sight they are. They are part of a greater system, a cosmic collaboration that keeps the rings alive, structured, and dynamic. The shepherd moons teach us something about the quiet power of small forces, the way subtle actions, over time, can create order out of chaos, and how even the most delicate, fragile systems can be sustained by the right balance of forces. These moons also give us a glimpse into the underlying mechanics of the universe, the invisible forces that shape everything around us. Gravity, in this case, becomes not just a force that pulls things down, but one that organizes, structures, and holds things together. It's not a heavy-handed force. It's more like a guiding hand that keeps everything in balance. And in the case of Saturn's rings, that balance is nothing short of beautiful. The shepherd moons keep the rings in motion, shaping them into those elegant arcs that we find so mesmerizing, and in doing so, they remind us that the cosmos is full of hidden interactions, of forces that are always at work, even when we can't see them. In the end, The shepherd moons are a perfect metaphor for how delicate and intricate the forces of the universe can be. They reveal how even the smallest entities, when placed in the right position and with the right force, can maintain the beauty and order of something as grand as Saturn's rings. It's a delicate symphony of motion, gravity, and subtle influence that creates something far greater than the sum of its parts. Ganymede, the largest of Jupiter's moons, holds a secret deep within its vast, icy surface: its magnetic field. It's an oddity in the solar system, standing out as the only moon known to have a magnetic field of its own, something we typically associate with planets, not their moons. But what really captures the curiosity of scientists isn't just the fact that Ganymede has a magnetic field, but the strength and density of it, which are unexpected given what we know about moons, especially one made mostly of rock and ice. There's something going on beneath Ganymede's surface that we don't fully understand, something that defies the usual expectations for how magnetic fields are generated. The source of Ganymede's magnetic field lies deep in its core, where scientists believe a molten metallic region, likely iron or iron-nickel, exists. On Earth, the movement of molten metal within our planet's core generates the magnetic field that protects us from solar radiation. The same process is thought to occur within Ganymede, but here's where things get puzzling. Ganymede is a moon, not a planet, and it's much smaller than Earth. It shouldn't have the kind of internal heat necessary to sustain the kind of core dynamo process that generates a powerful, stable magnetic field. And yet it does, which suggests that there's something different about the way Ganymede's interior works. Maybe it cooled more slowly than expected, or perhaps tidal forces from Jupiter keep its core warm enough to maintain this dynamo action. But there's another layer to this mystery. Ganymede's magnetic field is not just there. It's dense, much stronger than we would anticipate for a moon. The density of the magnetic field suggests that the processes generating it are more robust or unusual than we would expect. This raises questions about how Ganymede formed and evolved over time. Was it once a much hotter body, with an active core that generated a strong magnetic field early on, which has somehow been preserved? Or is there some unknown mechanism at play within Ganymede's interior that allows this field to be stronger than it should be for a moon of its size and composition? Adding to the intrigue is the fact that Ganymede's magnetic field interacts with Jupiter's immense magnetosphere in strange ways. Jupiter's magnetic field is the largest and most powerful in the solar system, dwarfing Earth's by a massive scale. Ganymede, being embedded within Jupiter's magnetosphere, shouldn't be able to sustain such a distinct, dense magnetic field of its own, at least not without being overwhelmed by Jupiter's. But somehow, Ganymede's field stands its ground, creating its own little magnetic bubble, a mini magnetosphere within the massive influence of Jupiter. It's like a small boat navigating within a raging river, somehow maintaining its own course amidst the overpowering currents. What's more, Ganymede's magnetic field contributes to auroras, those dancing lights we associate with polar regions on Earth. Ganymede has auroras too, and they flicker and shift as Jupiter's magnetic field pulls and tugs on Ganymede's own. These auroras provide clues to the strength of Ganymede's field and suggest that it's more complex than we first thought. The interaction between the two magnetic fields is almost like a conversation between a parent and a child. Jupiter's field dominates, but Ganymede's manages to hold its own, responding and reacting in ways that indicate a deep and complex internal structure beneath the icy surface. This magnetic density also leads scientists to wonder about Ganymede's subsurface ocean, which is another part of its mysterious interior. Some theories suggest that the interaction between Ganymede's magnetic field and its subsurface ocean could be key to understanding the moon's overall magnetic environment. If there is indeed a salty ocean beneath the thick ice, as many believe, it could conduct electricity and influence the magnetic field, perhaps even amplifying it in ways we don't yet fully understand. The ocean, hidden miles beneath the icy crust, might be playing a quiet but significant role in shaping Ganymede's magnetic signature. In many ways, Ganymede's magnetic field is like a story with missing chapters. We have pieces of the puzzle: its molten core, the interactions with Jupiter, the possibility of a subsurface ocean. But they don't quite fit together in the way we expect. There's something elusive, a piece of physics or geology that we haven't yet grasped, that keeps Ganymede's magnetic field from making sense in the conventional way. And that's what makes it so compelling. This massive moon, orbiting the largest planet in the solar system, is quietly holding onto secrets that challenge our understanding of how planets and moons work. For scientists, Ganymede's magnetic field is a reminder that the solar system still has plenty of surprises. It shows that even in places we think we understand, like moons orbiting gas giants, there are processes and dynamics that can catch us off guard. It's a place where the usual rules don't always apply, where something as seemingly straightforward as a magnetic field becomes a doorway to deeper questions about the moon's formation, its internal structure, and its connection to its giant host planet. Ganymede's magnetic field feels almost alive, like a force that has persisted against the odds, defying expectations of what a moon should be capable of. And as we continue to study it, we get the sense that Ganymede has more to reveal, that the density of its magnetic field is not just a scientific curiosity but a clue to a much larger story about the moon's origins and its ongoing evolution. There's a quiet persistence in Ganymede, a subtle defiance of the norms we expect from a world so far from the sun, that keeps drawing us back to study it further, hoping to uncover the full truth behind its magnetic heart. Jupiter's radiation belts are a force to be reckoned with. Unlike anything we experience on Earth, they are vast regions of space, swirling with charged particles that move at near-light speed, forming an invisible but deadly storm of radiation around the giant planet. These belts are among the most intense in the solar system, capable of frying any spacecraft that ventures too close without proper shielding. They represent a world where the usual limits of space, silent, cold, and empty, are replaced with something far more dangerous and dynamic. But the origin of these radiation belts is as much a product of Jupiter's immense size and power as it is of the planet's magnetic field, its moons, and even the solar wind. At the heart of Jupiter's radiation belts lies its magnetic field, which is staggeringly powerful, about 20,000 times stronger than Earth's. This magnetic field extends far into space, trapping charged particles, mostly electrons and protons, that get caught in its web. These particles come from a variety of sources, and their origins are key to understanding the belt's intensity. One source is the solar wind, a constant stream of particles emitted by the sun. When the solar wind reaches Jupiter, its particles are funneled into the planet's magnetosphere, where they are accelerated by the magnetic field and added to the already churning radiation belts. But the sun is only part of the story. Jupiter's own system contributes significantly to these radiation belts, and one of the main culprits is its volcanic moon, Io. Io is the most volcanically active body in the solar system, constantly spewing sulfur dioxide into space. This material gets ionized, turned into charged particles, by the intense radiation near Jupiter, and these ions are then caught up in the magnetic field, swirling around the planet in enormous numbers. As Io orbits Jupiter, it acts almost like a factory for charged particles, continuously feeding Jupiter's radiation belts with fresh material. The interaction between Io and Jupiter's magnetosphere is so powerful that it creates electric currents that flow between the moon and the planet, sparking auroras on Jupiter's poles and fueling the belts with even more energy. But the belts themselves aren't static. They're constantly in motion, shaped by the forces of Jupiter's magnetic field and the solar wind. The particles within the belts are accelerated to near-relativistic speeds, moving so fast that they become deadly to anything unprotected. These particles collide with one another and with Jupiter's atmosphere, emitting intense radiation in the process. It's a cycle of energy that never seems to stop, with the belts acting almost like a giant particle accelerator that never powers down. In fact, the belts are so intense that they pose a significant challenge to any spacecraft that tries to explore Jupiter. NASA's Juno mission, for example, had to take great care in how it approached Jupiter, timing its orbits to avoid the most dangerous regions of the radiation belts. Jupiter's radiation belts also have a way of reshaping our understanding of what it means to explore outer space. They're not just invisible hazards, they are physical manifestations of the planet's immense power. Jupiter, with its enormous magnetic field and its moons, has created a kind of natural barrier, a space filled with energy and danger that reminds us how small and fragile our technology can be in the face of such forces. The belts act as a sort of moat around the planet, a reminder that exploring the outer solar system requires not just curiosity but respect for the immense power these distant worlds wield. What's particularly interesting about Jupiter's radiation belts is that they're a product of both internal and external forces. Internally, Jupiter's rapid rotation, spinning once every 10 hours, creates a powerful dynamo effect within its metallic hydrogen core. This dynamo is what generates the planet's magnetic field in the first place. But externally, the radiation belts are shaped by interactions with the Sun, its moons, and the cosmic environment around it. It's as if Jupiter's radiation belts are a cosmic balancing act, influenced by forces that span from the Sun all the way down to the volcanic eruptions of Io. The belts are a dynamic system, constantly evolving as new particles are added and accelerated, while others are lost into space or absorbed by the planet's atmosphere. From a human perspective, Jupiter's radiation belts are both a marvel and a threat. They represent the sheer scale of power that exists in the universe, forces that operate on a level far beyond anything we experience on Earth. The radiation belts show us that even something as seemingly simple as a planet's magnetic field can create environments that are hostile, dangerous, and incredibly complex. And yet, there's a certain beauty to them as well. A reminder that the universe is full of extremes, places where the laws of physics take on new, almost fantastical forms. Jupiter's radiation belts are a vivid example of how powerful and untamed the outer solar system can be, and how, in the vastness of space, there are still forces beyond our control or full understanding. Ultimately, the origin of Jupiter's radiation belts is a story of interconnected forces. It's a story that begins with the planet's internal dynamo, fueled by its rapid rotation and massive core, but it's one that expands outward to include the Sun, the solar wind, and even the volcanic activity of its moons. It's a reminder that in space, nothing exists in isolation. Everything is part of a larger, more complex system. Jupiter's radiation belts are a product of this system, a testament to the planet's enormous influence on its surroundings, and a sign of the dynamic and sometimes dangerous forces that shape the outer planets. Iapetus, one of Saturn's strangest moons, stands out with its striking two-tone appearance. One side is bright and icy, while the other is as dark as coal. It's almost as if this moon wears a mask, split between two faces, each reflecting a completely different personality. Imagine standing on its surface, feeling the sharp contrast beneath your feet. One moment, you're bathed in the blinding white light reflecting off an ice-covered landscape, and the next, you're swallowed in the inky blackness of a side that seems to absorb the starlight. This dramatic difference in coloration is one of the great mysteries of our solar system. The bright side of Iapetus, known as the leading hemisphere, reflects about 50% of the sunlight that strikes it, covered in water ice that has remained relatively pristine. But turn to the other side, the trailing hemisphere, and you're met with a dark, almost soot-like surface that reflects less than 5% of the sunlight. It feels as if you've crossed into another world entirely. This darkness is thought to come from a fine dusting of material from another of Saturn's moons, Phoebe, which may have coated Iapetus over millions of years. Some theorize that this dark material began to collect on Iapetus as it orbited Saturn, slowly accumulating and making the contrast sharper with every passing eon. It's as though this moon has two faces, one forever trying to conceal itself, the other glaringly exposed to the light. But it's not just an aesthetic curiosity. The dark material absorbs more heat, causing that side of the moon to warm up slightly. Over time, this warming has led to a kind of runaway effect. Ice on the dark side sublimates, turning directly from solid to gas, leaving even more of the dark material behind, while the water vapor migrates to the colder, bright side and freezes there. It's a celestial dance of contrast, a slow-motion transformation that has likely been occurring for billions of years. Iapetus also has a shape that's just as peculiar as its coloration. Its equator is marked by a massive ridge, a feature so bizarre it has been compared to a walnut in appearance. This ridge runs almost the entire circumference of the moon, rising up to 12 miles high in some areas. No other moon in the solar system has a feature quite like it. There's speculation about how it formed. Perhaps it was once a ring system that collapsed onto the moon's surface, or maybe it's the result of Iapetus cooling and shrinking early in its history. Walking along this ridge, you might feel as if you're traversing the spine of some ancient, forgotten creature, its towering peaks casting shadows on either side, dividing day from night. In the larger scheme of things, Iapetus feels almost forgotten, quietly orbiting Saturn with its secrets intact. The two-tone coloration and the ridge raise deep questions about its history. Was it once more active, more chaotic? Did it go through a traumatic past, bombarded by debris from Saturn's violent rings or torn apart by gravitational forces? Its mysteries are locked away in the cold, the dust, the ice, whispers of a past no one remembers. Yet, for all its oddity, there's something almost human in its nature. It's divided, caught between extremes, light and dark, warm and cold, never truly one or the other. It's a place of contrasts, where every step would feel like crossing a boundary, from the bright, reflective landscapes to the deep, shadowed regions. And like so many contradictions in the universe, Iapetus refuses to reveal all its secrets. It's there, on the far side of Saturn, waiting to be understood. A reminder that even the most remote and silent places in the cosmos carry the scars and mysteries of a long, unknowable history. It is a place where duality exists not only in appearance, but in the story it tells. A story where light and dark are forever locked in a quiet, cosmic battle. Beneath the swirling clouds of Saturn, a quiet but persistent enigma radiates from its south pole, an unexpected and unexplained source of heat. Unlike the gentle warmth we might associate with sunlight or the familiar heat rising from the Earth's surface, this is something far stranger. Imagine being close to the planet, with its majestic rings casting shadows across the vast gas giant, and noticing that something at its southern end doesn't fit the natural order. It's as though Saturn is quietly exhaling warmth, but only from one specific part, as if keeping a secret close to its core. What makes this heat emission so strange is how localized it is, a tight concentration of warmth rising from the pole while the rest of Saturn remains enveloped in its cold, distant outer atmosphere. The temperatures at the planet's poles should, by all accounts, mirror the icy chill that dominates its overall environment. Yet here, we find the opposite. It's as if Saturn itself is ignoring the frigid depths of space, breaking the rules we think we understand about how such worlds should behave. Saturn's south pole is marked by a massive hurricane-like storm, a whirling vortex of clouds that seems to deepen the mystery. At its center, there's an eye-like formation, spinning relentlessly within the atmosphere. This storm might feel like a manifestation of the heat, as if the planet's internal energy is being funneled upward and out, concentrating at the pole. But even with that explanation, something more elusive seems to be at play. Saturn's core, buried deep beneath the thick, gaseous layers, might be leaking energy outwards. But why does it choose the South Pole as its gateway? Why does the heat focus there rather than being evenly distributed across the planet? Theories swirl around this phenomenon. Some suggest that Saturn's interior, where pressures and temperatures are unimaginably high, could be releasing stored energy in a slow, creeping way. Maybe there's a flow of material beneath Saturn's clouds that channels the heat toward the pole, like a river running through invisible cracks in the atmosphere. Others think it might be connected to complex interactions between Saturn's magnetic field and the solar wind, somehow triggering this burst of warmth. But none of these ideas fully capture the strangeness of the reality. A singular, concentrated heat source in a place where cold should reign. There's something almost alive about it, like the planet itself is restless, with energy building up deep inside and spilling out through this pole. If you were there, floating above the swirling storm, you'd feel the dissonance between what your senses tell you and what logic says should exist. The towering storm clouds might carry with them a whisper of warmth, defying the icy winds of space, hinting at some deeper, unexplained source of power. Some of the heat might be the result of compression within Saturn's atmosphere, a kind of squeezing effect as gases move and churn in the depths. But that's only a part of the answer. The true source remains hidden, cloaked by the layers of gas that make up Saturn's enormous body. And even though we've sent probes and telescopes to study it, the deeper secrets of this heat remain locked away, inaccessible. It's easy to anthropomorphize Saturn in this context, imagining it as a living entity, shifting and moving beneath its layers, unable to remain perfectly still. Like a person releasing a quiet sigh, this heat emission might be a glimpse into the planet's inner workings, something deep and unseen, quietly pressing outward. The South Pole becomes a focal point, a place where Saturn's internal mysteries make their way to the surface, albeit in ways that don't yet align with our understanding. This unexplained heat adds another layer to the complexity of Saturn, a planet already full of contradictions and wonders. It defies easy explanation, much like so many of the most fascinating things in the universe. The warmth radiates outward, a subtle reminder that not all energy is visible or easy to grasp. Some things just lie in waiting, tantalizingly out of reach, daring us to find out more. And as the warmth continues to rise from Saturn's pole, we are left to wonder what else the planet might be hiding, what other mysteries might be brewing beneath its swirling clouds, waiting to be discovered. Far beyond the reaches of the sun's warmth, in the cold, distant region of our solar system, Neptune's moon Triton holds onto a secret that whispers of life where none should exist. A possible ocean hidden beneath its frozen, icy crust. The idea of an ocean there, so far from anything familiar, is both mesmerizing and puzzling. Triton, with its barren, frost-covered surface, feels like the last place you would expect to find water in its liquid form. Yet, under that thick layer of nitrogen ice, there might be a vast, hidden ocean, quietly existing in the dark, cut off from the sun and the empty void of space. To stand on Triton's surface would be to confront an alien world of extreme contrasts. The cold would bite at your skin, colder than anything you could experience on Earth, with temperatures plunging to nearly absolute zero. Geysers of nitrogen gas would erupt into the thin atmosphere. A strange reminder that this moon, despite its outward stillness, is very much alive. But the most intriguing part of Triton is what lies beneath its frozen exterior. If you could dig deep enough, you might eventually reach something unexpected. A world of liquid water, trapped below the surface for billions of years, insulated by the very ice that imprisons it. This ocean, if it exists, isn't simply the product of chance. Scientists believe that tidal forces, exerted by Neptune's immense gravity, stretch and squeeze Triton as it orbits its parent planet. These forces generate heat within the moon's interior, warming the ice from the inside out. The friction from this constant tugging might be enough to melt the lower layers of Triton's ice, creating an ocean beneath its frigid surface. It's an eerie thought. Water, the element we so often associate with life, lying in wait under layers of ice on a moon so far removed from the sun's warmth. Imagining what could exist in such an ocean evokes images of otherworldly life forms, perhaps surviving in environments so harsh they make Earth's deepest oceans seem like a tropical paradise. If there are vents at the bottom of this hidden ocean, where heat seeps from the core, it's possible that microorganisms, or something even more complex, could be thriving, living off the chemical energy released by these vents. Just as life on Earth has been found around hydrothermal vents in the darkest parts of our oceans, could the same hold true for Triton? Triton is unique in other ways too. Unlike most moons in the solar system, it orbits Neptune in the opposite direction, a retrograde motion that suggests it wasn't originally part of the planet system. It may have been captured long ago, a wandering object pulled in by Neptune's gravity, forever changing its destiny. This backstory only adds to Triton's allure. If it was once a rogue object, possibly originating from the Kuiper Belt, then it might carry secrets from the farthest reaches of the solar system, a frozen vault of ancient material and mysteries that have remained untouched for eons. The existence of a subsurface ocean would transform Triton from a cold, distant moon into a place brimming with possibilities. What if it's a reservoir of life, locked away beneath its icy shell? Or what if the ocean itself is a relic of a time when Triton roamed freely through space, before it was captured by Neptune? In either case, this hidden ocean could be a key to understanding not only Triton's past, but also the broader question of life beyond Earth. In a sense, Triton mirrors our own fascination with the unknown. It's a place that holds its secrets tightly under layers of ice so thick and so cold that they seem impenetrable. Yet, beneath that icy barrier might be a thriving, liquid world, a world that's out of sight but never fully beyond the realm of our imagination. It's a reminder that even in the most desolate corners of the solar system, the potential for life persists, hidden away in the most unlikely places. We look at Triton, and we can't help but wonder what might be waiting for us, just below the surface. Io, Jupiter's most tortured moon, is a world where the ground is never still. If you were to set foot there, you'd find yourself in a place of constant upheaval. Volcanoes erupting with such ferocity that they could swallow cities, lakes of molten lava stretching out for miles, and geysers of sulfurous gas shooting hundreds of kilometers into the blackness of space. The landscape would feel both violent and surreal, more alive and active than any place you've ever seen, as though Io itself were burning from the inside out. This relentless volcanic activity is driven by forces that are far beyond Io itself. Trapped in a gravitational tug-of-war between Jupiter and its neighboring moons, Io is caught in a brutal dance. The immense gravity of Jupiter pulls on Io's core, while the orbits of Ganymede and Europa, two other large moons, create opposing forces that twist and stretch the moon. The result is a kind of planetary kneading, where Io's insides are constantly churned, generating heat so intense that the surface cracks open again and again, unable to hold the molten rock beneath it. This internal turmoil makes Io the most volcanically active body in the solar system, by far. Standing on Io, the sky would be dark, punctuated by the looming presence of Jupiter, whose massive bulk dominates the view. It would hang there like a giant, pulling on every fiber of your being, almost as if you could feel the gravitational strain Io endures with every orbit. The moon's surface, though, is a kaleidoscope of colors. Sulfur, ash, and volcanic debris cover the landscape, painting the terrain in yellows, oranges, reds, and blacks. The air would be thick with the stench of sulfur, and you'd find yourself surrounded by towering plumes of volcanic ash rising into space, some so large they can be seen from Earth. The eruptions on Io are not just violent, they are continuous. Unlike Earth, where volcanoes erupt sporadically, here the entire surface is reshaped by almost constant volcanic activity. Some of these eruptions are so powerful that they send lava fountains miles above the surface, while others spill rivers of molten rock across the moon's landscape, forming lakes that can remain molten for years. Walking across Io's surface would feel perilous, as if the ground beneath your feet could open up at any moment, swallowing you in a burst of molten sulfur. The sheer scale of Io's volcanic activity makes it unlike any place we've ever encountered. Some of its volcanoes, like Loki Patera, are massive, covering areas larger than entire countries. They erupt with such force that they dwarf even the most powerful eruptions in Earth's history. And yet, despite the chaos, there's a strange, underlying rhythm to Io's eruptions, driven by the gravitational forces that pull on it like clockwork. This constant reshaping means that Io has no permanent surface features. Everything is temporary, constantly buried or obliterated by the next volcanic blast. Beneath all this activity, Io's interior is a molten, churning cauldron of magma, heated by the relentless squeezing and stretching caused by tidal forces. It's this internal energy, continuously generated by Jupiter's gravitational pull, that makes Io so volcanically active. In many ways, it's as though the moon has no choice in the matter. Its fate was sealed the moment it was locked into this gravitational battle with its neighboring moons and their massive parent planet. But for all its chaos, Io isn't just a place of destruction. It's also a place of creation. Each eruption adds new layers to the surface, new landscapes formed in the blink of an eye. Lava flows harden into solid rock, geysers of sulfur create vast plains of new material, and mountains rise and fall in the geological blink of an eye. The constant reshaping of Io makes it a place of endless transformation, where nothing stays the same for long, and every moment brings with it the birth of something new. Yet, for all the power and violence, there's something tragic about Io. It is locked in a struggle it cannot escape, forever torn between Jupiter's pull and the forces within it, condemned to an existence of unrelenting upheaval. It's a place that feels both alive and exhausted, constantly creating and destroying itself, its surface never allowed to settle, its core forever roiling with energy. But in this turmoil, there's also a kind of beauty, a reminder that even in the most extreme environments, the forces of nature continue to work, reshaping, reforming, and building in ways that are both familiar and utterly alien. Hyperion is a moon that defies expectations. Unlike most of the rounded, spherical moons we've come to expect orbiting planets, Hyperion looks more like a battered, cosmic sponge. Its shape strange and irregular, as if it were never given the chance to become whole. Imagine floating near it, seeing a world that appears almost haphazard, its surface covered in deep craters that pockmark its entire face, while its overall form twists and turns, more an asteroid than a moon. There's a sense that Hyperion wasn't fully formed, as though some violent event in the past left it frozen in this unfinished state. Its irregular shape likely comes from a history of collisions and impacts. Hyperion was probably part of a larger body at some point, a piece of something much greater that was shattered in the distant past. The remnants coalesced into this bizarre moon, left to drift in Saturn's orbit, its jagged edges and uneven surface standing as a testament to its chaotic origins. If you could touch its surface, it would feel almost hollow, its low density suggesting that much of Hyperion is empty space, with huge pockets of porous material making it one of the least dense moons in the solar system. It's as if the moon is more whole than rock, a brittle, airy object that barely holds itself together. Up close, Hyperion's surface would feel both alien and strangely familiar, covered in deep craters that seem to reach into its core. These craters are unlike the smooth, weathered ones seen on other moons. They appear sharp and jagged, with walls that are steep and shadows that are deep. Each crater seems like a wound left open, unhealed. Over time, cosmic debris has bombarded Hyperion, leaving it with more craters than smooth surfaces, as if the moon were slowly being carved away. The low gravity on Hyperion means that material blasted off its surface during impacts doesn't settle back down, leaving the moon looking raw and scarred. What adds to Hyperion's strangeness is its unpredictable spin. Most moons rotate in a stable, predictable way, locked into patterns of rotation by the gravitational forces of the planets they orbit. But not Hyperion. Its irregular shape throws off its balance, causing it to tumble erratically through space. If you watched it over time, you'd see no regular rotation, no familiar rhythm to its movement. One moment, one side of the moon might face you, but moments later, without warning, it would twist away, turning chaotically as it orbits Saturn. This tumbling motion makes Hyperion feel alive in a way that most moons do not, like it's constantly unsettled, unable to find peace in its orbit. The idea of walking on Hyperion's surface feels impossible in a practical sense. Its weak gravity would barely keep you grounded, and its erratic spin would leave you disoriented. But if you could stand there, looking out across its rugged, cratered landscape, you might feel a sense of disconnection from everything you've known about moons and planets. Hyperion doesn't play by the rules, and it doesn't fit into the neat categories we often use to understand the cosmos. Its existence feels like an outlier, a leftover fragment of a much more chaotic time in the solar system's history. Hyperion's connection to Saturn is also complex. It's not a close companion like some of the larger moons, orbiting at a more distant range, and yet it is profoundly influenced by its giant host. Saturn's gravity, along with that of its other moons, plays a role in Hyperion's odd behavior, adding to the moon's instability. But for all its eccentricity, there's a certain beauty in Hyperion's defiance. Its uneven shape and unpredictable nature make it stand out in a solar system filled with orderly, spherical moons, as if it's chosen to be different, to reject the smooth, polished appearance of its neighbors. This moon, with its spongy appearance and tumbling motion, is a reminder that not everything in the universe follows a perfect path. Some objects remain forever strange, forever irregular, resisting the gravitational forces that try to mold them into something more familiar. Hyperion, in its oddity, seems to represent a kind of cosmic rebellion, an object left over from an earlier, wilder time, still carrying the scars and the chaos of its birth, spinning unpredictably through space, never quite fitting into the neat, expected patterns of the universe. Far from the familiar light of the sun, deep within the atmospheres of Neptune and Uranus, a phenomenon might be taking place that feels like something out of a dream. Rain made of diamonds. It's hard to imagine, but in the crushing depths of these distant ice giants, the conditions are so extreme that carbon atoms are thought to be squeezed and compacted into diamond crystals, which then fall like rain through the swirling clouds of methane and hydrogen. If you could somehow survive the descent into this alien atmosphere, you'd witness something utterly unlike anything on Earth. Not soft droplets of water, but hard, sparkling stones falling silently through a dense, ghostly fog. The atmosphere of these planets is nothing like the thin, familiar air of Earth. As you travel deeper, the pressure mounts at a level incomprehensible to us, thousands of times greater than the surface of our own planet. Temperatures climb, too, reaching thousands of degrees. And it's in this hellish combination of intense heat and overwhelming pressure that something remarkable happens. Methane molecules, abundant in the atmospheres of Neptune and Uranus, are broken apart by the pressure, freeing carbon atoms. These atoms are then forced together by the sheer weight of the atmosphere above them, compacted into crystals of pure diamond. In the depths of these planets, diamonds don't sit in mines, locked in rocks. They fall from the sky. The idea of diamond rain stretches the imagination. Picture these carbon crystals, heavier than the surrounding gas, beginning their slow fall, tumbling through layers of the atmosphere. Each diamond would be microscopic at first, but as it descends, it might grow larger and more solid, until it becomes a pebble, then a stone. Eventually, these diamonds would gather into great clouds, drifting downwards in vast numbers, creating a dazzling but deadly rainstorm that never sees the light of day. The diamonds would continue to sink, settling deeper into the planet's interior, where they might eventually dissolve or form new layers of the planet itself. This process would be continuous, an endless cycle of creation and transformation as Neptune and Uranus quietly manufacture diamonds within their depths. But it's not the kind of beauty that could ever be seen up close. To reach the depths where diamond rain occurs, you'd need to pass through layers of freezing winds and blinding storms of hydrogen and helium, until the pressure became so great that it would crush anything human-made long before you ever reached the diamonds themselves. Even in theory, getting close enough to witness this rain would mean certain destruction for any machine, let alone a person. Yet, despite the inaccessibility of these glittering clouds, the idea of diamond rain is based on very real science. Experiments conducted on Earth have shown that under conditions similar to those found on Neptune and Uranus, methane can indeed break apart and form diamonds. It's a tantalizing hint that beneath the blue and green haze of these distant planets, there's a hidden, ongoing process that turns the most common element, carbon, into the most coveted of gems. But these diamonds are not for the taking. They are locked within the very structure of the planets themselves, forming part of an alien geology that we can only guess at from afar. This rain of diamonds also raises profound questions about the nature of planets like Neptune and Uranus. These ice giants, while cold and distant, are far more complex and dynamic than we once thought. They aren't just frozen, inert worlds. They are places of intense heat, crushing pressure, and strange chemical transformations. Beneath their calm exteriors, entire oceans of liquid diamond may exist, with stones the size of boulders drifting silently through the planet's interior, their journey never ending. Each one a part of a process billions of years in the making. But perhaps the most fascinating aspect of the diamond rain is the realization that even in the most extreme environments, the universe finds ways to create beauty. What seems like an unimaginable landscape, a place where diamonds fall like rain, is a natural byproduct of the forces at work deep within these planets. The diamond rain on Neptune and Uranus is a reminder that the universe is full of wonders we can barely understand, and that sometimes the most extraordinary phenomena happen in places we may never see. These diamonds, created by forces far beyond our control, are part of a cosmic dance transforming the planets themselves in ways both mysterious and sublime. Jupiter's irregular satellites move in ways that seem to defy the predictable rhythms you might expect from moons bound to such a massive planet. Unlike the Galilean moons, Io, Europa, Ganymede, and Callisto, which orbit in neat, circular paths close to Jupiter, these outer satellites are wild. Their orbits stretched into long ellipses, tilted at bizarre angles, and sometimes even spinning in the opposite direction of the planet's rotation. It's as if these moons were caught in a gravitational dance they never quite belonged to, always slightly out of sync with the rest of the solar system. These irregular orbits tell a story of capture rather than birth. While Jupiter's larger, more familiar moons likely formed from the same swirling disk of gas and dust that gave rise to the planet itself, the irregular satellites have a different origin. Many of them are thought to have once been wandering through space, asteroids or chunks of rock, drifting through the early solar system in chaotic paths of their own. And then, at some point in their distant past, they crossed paths with Jupiter, whose immense gravity reached out and pulled them into its orbit, capturing them like a spider catches flies in its web. But the process of capture wasn't smooth. Instead of settling into regular, circular orbits, these moons were left in the strange, off-kilter paths they now follow, forever marked by the violent process that brought them into Jupiter's fold. The irregular satellites come in groups, some with orbits that cluster together in similar patterns, suggesting they share a common origin. Perhaps they were once part of a larger object that was shattered by a collision, either with Jupiter itself or with another captured moon. This violent history means that many of these satellites are small, jagged, and irregularly shaped, more like battered remnants than fully formed moons. Their paths are unstable, and some may eventually be flung out of Jupiter's orbit altogether, continuing their journey through the solar system alone once more. What's striking about these moons is their sheer variety. Some, like Sinope and Pasiphae, follow retrograde orbits, moving in the opposite direction to the planet's rotation. Others, like Carmi and Ananke, are part of larger families of moons that share similar inclinations and eccentricities, suggesting they were once pieces of the same body, torn apart by ancient impacts. The distances these moons travel from Jupiter are vast compared to the planet's inner moons, and the tilted angles of their orbits mean they spend most of their time far above or below Jupiter's equatorial plane, almost like they are outcasts from the main family of moons. Imagine standing on one of these distant, irregular satellites. Jupiter would loom impossibly large in the sky, yet the moon itself would feel disconnected from the planet it orbits. The path you travel through space would feel unpredictable, a long, looping journey that swings you far from Jupiter before bringing you back and close again. Each time you orbited, you'd see the planet from a different angle, as your path twists and turns through the gravitational field that once captured you. There would be no feeling of stability, no sense that this was ever a permanent home. But there's a kind of beauty in the chaos of these orbits. It's a reminder that the early solar system was a place of violent collisions and sudden gravitational shifts, where worlds were constantly forming, breaking apart, and being reshaped by forces far beyond their control. The irregular satellites are relics of that time, survivors of the early solar system's chaos, still carrying the scars of their violent pasts. They orbit Jupiter in paths that may one day change again, as gravitational forces from the planet, or from other moons, nudge them into new trajectories, or perhaps even eject them from the system altogether. Their irregular orbits speak of a time when the solar system was still young, a time when everything was in flux and the gravitational pull of a planet like Jupiter could change the fate of any wandering body that came too close. And now, millions or even billions of years later, these moons still carry the legacy of that era, orbiting in ways that seem almost defiant, as if they've never fully settled into their new lives around the giant planet. Uranus, with its pale blue-green hue, seems peaceful from a distance, a planet that appears almost dormant in its stillness. But as time passes, it reveals that something more complex is unfolding beneath that calm facade. Its atmosphere, seemingly static, goes through dramatic seasonal changes that we are only beginning to grasp. The strangeness starts with the planet's extreme tilt, a 98-degree angle that leaves Uranus almost lying on its side as it orbits the Sun. This unique orientation creates seasons unlike anything experienced on Earth, where entire hemispheres are plunged into darkness or light for decades at a time. As Uranus makes its 84-year journey around the Sun, the extreme tilt means that its poles experience summer and winter in the most intense ways imaginable. One pole is bathed in continuous sunlight for 21 years, while the other remains in the shadow of an unending winter. This cycle alone would suggest that any atmospheric changes on Uranus would be slow and predictable, changes happening over the course of decades as each pole takes its turn in the sunlight. But instead, something more puzzling is happening. Even when the sunlight reaches different regions of Uranus, the atmosphere seems to react in ways that defy straightforward explanation. For much of the time Uranus was observed in the 20th century, its atmosphere seemed relatively calm, with few visible clouds or storms. But as it approached its equinox in 2007, something unexpected happened. The planet's atmosphere suddenly became more active, with bright clouds and storm systems appearing. It was as if Uranus had woken up from a deep slumber, and the question of what triggered these changes became more pressing. The planet's distance from the Sun means that solar energy reaching Uranus is minimal, and yet, these seasonal changes suggest that something else is stirring deep within. The mystery lies in what causes such dramatic shifts in an atmosphere that receives so little energy from the Sun. Could there be internal processes at play? Something happening beneath Uranus's icy clouds that drives these shifts? Some scientists speculate that the planet's core may be more dynamic than previously thought, releasing heat in irregular pulses that stir the upper atmosphere. Others wonder if the extreme tilt causes Uranus's atmosphere to behave differently from other planets, leading to strange seasonal effects that we don't yet understand. These changes can be seen in the planet's cloud formations. During certain times of the Uranian year, bright spots appear in the planet's atmosphere, storms that rise and dissipate without warning. They form not just at the poles where the sunlight is expected to cause the most change, but even at the equator, where the sunlight should be minimal. These atmospheric outbursts hint at processes going on beneath the surface, processes that defy easy explanation. It's as if Uranus, for long periods, hides its true nature, only to briefly reveal glimpses of activity that we can't fully explain. If you could witness the seasonal changes on Uranus firsthand, you would see a world transformed not by quick shifts, but by a slow, unfolding drama that spans decades. As the planet moves through its orbit, the clouds would subtly change, and over time, entire regions of the planet would either emerge from darkness or sink into it. The appearance of storms and cloud formations would be sudden, but they would happen against the backdrop of long, slow transitions, as if the atmosphere itself is caught in a cycle that we're only beginning to comprehend. The real enigma of Uranus's seasonal changes is the question of how a planet so distant, receiving such limited solar energy, could experience such profound atmospheric shifts. There's a quiet unpredictability to Uranus, a planet that defies easy classification, with its tilted axis, its hidden storms, and its unexplained changes. It leaves us with more questions than answers, as though its seasonal transformations are a mystery that will take many more decades, or even centuries, to fully unravel. Each observation of Uranus during its long journey around the Sun feels like catching a glimpse of a much larger story, one that stretches far beyond human lifetimes. The planet's strange seasons may be part of a complex interplay of forces, gravitational, solar, and internal, that we are only beginning to perceive. And yet, as baffling as these changes are, they are a reminder that even in the farthest reaches of our solar system, planets are not static. They evolve, shift, and reveal new layers of complexity that keep challenging our understanding of the cosmos. Neptune's atmosphere is a place of constant motion, where swirling bands of clouds and storms shift and transform in ways that are both mesmerizing and confounding. From a distance, Neptune looks serene, its deep blue color suggesting a world at peace. But up close, it's anything but calm. Neptune is the windiest planet in our solar system, with gusts that can reach speeds of 1,200 miles per hour, fast enough to tear apart any structure we could imagine. The bands that stripe Neptune's atmosphere move with this incredible speed, sometimes visible as bright, white streaks in the planet's upper layers, while dark storms spin across its surface like massive whirlpools. What's so fascinating is how these atmospheric bands seem to shift over time. They don't stay locked in place the way Jupiter's bands do. Instead, they appear to wander across the planet's surface, shifting in latitude, sometimes disappearing altogether only to reappear elsewhere. It's like watching a living, breathing entity, with clouds that pulse and swirl, forming and dissipating with a rhythm that seems random yet feels alive with an energy all its own. If you could stand on Neptune, though of course no human could survive its crushing winds and frigid temperatures, you would see a sky constantly in motion. Vast cloud formations would race across the horizon, stretching for hundreds of miles, then breaking apart in a matter of hours. These clouds are made of methane ice, reflecting sunlight in ways that give Neptune its characteristic glow. But the movement of the clouds is chaotic, unpredictable. They seem to follow the wind patterns of the planet, yet they also shift independently, as if driven by some unseen force deep within Neptune's atmosphere. The real mystery lies in why these bands and clouds shift in the first place. Neptune is far from the Sun, receiving only a fraction of the energy that fuels the atmospheric changes on Earth or even on Jupiter. And yet, its atmosphere is one of the most dynamic in the solar system. Some scientists believe that internal heat plays a major role. Neptune, like its icy twin Uranus, generates more heat than it receives from the Sun. This internal energy may rise up from deep within the planet, creating the turbulence that causes clouds to form and shift across the surface. This shifting of bands and clouds is also linked to Neptune's storms. The planet is famous for its Great Dark Spot, a massive storm system akin to Jupiter's Great Red Spot, though far more transient. These dark spots, sometimes large enough to swallow Earth, appear in the atmosphere and can last for years, only to vanish without a trace. It's possible that these storms play a role in disrupting the atmospheric bands, redistributing the clouds and gases as they move. When the storms dissipate, they leave behind a planet that looks different than before, with bands and clouds that have moved to new locations or even new latitudes. But the mystery deepens when we consider how little we know about Neptune's atmosphere beneath the visible clouds. The upper layers give us a glimpse of shifting patterns, but what lies below remains hidden, inaccessible. It's possible that deeper winds and currents are driving the changes we see on the surface, with immense pressure and temperature differences creating currents that rise and fall over time, pushing the clouds above them into new and unexpected patterns. Over the years, as we've continued to observe Neptune, we've noticed long-term changes that suggest even larger forces at work. Some cloud bands that were once prominent have faded, while new ones have emerged. These shifts seem to occur in cycles, though we don't yet fully understand what triggers them or how they are connected to the planet's internal structure. It's as if Neptune's atmosphere is caught in a delicate balance, responding to forces both within and beyond the planet itself, with the sun's distant light barely influencing the swirling chaos beneath. Neptune's atmospheric bands and shifting clouds are a reminder of the planet's untamed nature, a world shaped by forces we can barely comprehend. Watching these changes unfold, it feels as though we're observing a distant storm from a place of safety, marveling at its power and unpredictability. Yet Neptune is so far away, and the time it takes for changes to happen on such a massive scale is beyond our everyday experience. The planet's atmosphere shifts in ways that reflect both the quiet passage of time and the violent, restless energy within it. A world in constant motion, driven by the unseen forces of its deep, blue heart. Imagine standing in the vast emptiness of space, with Saturn hanging like a giant in front of you, its rings casting long shadows over the planet. You wouldn't hear much in the vacuum, but if you had a radio tuned just right, you'd pick up something eerie, strange, almost melodic sounds coming from Saturn. These radio emissions are unlike anything you'd hear on Earth. They're not like the typical signals from stars or planets. They pulse, almost sing, with a rhythm that feels strangely alive. These emissions have puzzled scientists for decades, their origins shrouded in mystery, as if Saturn itself is trying to communicate, its voice carried on invisible waves through the cosmos. The source of these haunting signals lies deep within Saturn's magnetic field. Saturn, like Earth and Jupiter, has a powerful magnetosphere, an enormous bubble of magnetic energy that traps particles from the solar wind. As these charged particles spiral along Saturn's magnetic field lines, they interact with the planet's upper atmosphere, causing disturbances that generate radio waves. But the emissions aren't simple, monotonous hums. Instead, they vary, crackling with bursts of intensity, as though the magnetic field is alive with activity, constantly shifting and evolving. It's easy to think of Saturn as just a giant gas ball surrounded by rings, but its magnetosphere adds another layer of complexity. The interplay between its magnetic field, the solar wind, and its moons, especially the icy Enceladus, creates a dynamic environment that constantly churns with energy. Enceladus, in particular, plays a key role. The moon releases plumes of water vapor and ice particles from its subsurface ocean, and as these particles are caught up in Saturn's magnetic field, they disrupt the flow of energy, triggering bursts of radio waves that sweep across space. If you could hear Saturn's radio emissions, they would sound like the planet's heartbeat, irregular but constant, pulsating as it reacts to the forces around it. Every so often, you'd catch a spike, a sudden, sharp increase in the signal, as a solar storm slams into Saturn's magnetic field, or a fresh burst of material from Enceladus disrupts the delicate balance. The sound would change with time, reflecting the shifts in Saturn's space environment, almost like a symphony conducted by forces far beyond our control. What makes these emissions even stranger is their variability. Over time, they change in ways that don't always correlate directly with solar activity or the moon's interactions. It's as though the magnetosphere has moods of its own, influenced by processes deep within Saturn's atmosphere or core. Some scientists suspect that the rotation of Saturn itself, with its rapid spin, might play a part in modulating these radio waves. Others think that deeper currents of charged particles, far beneath the clouds, might rise up occasionally, adding to the symphony. Then there's the question of how these emissions relate to the mysterious auroras that dance around Saturn's poles. Much like Earth's northern lights, Saturn's auroras are created when particles from the solar wind are funneled into the atmosphere along magnetic field lines. But Saturn's auroras are far more intense, and they too seem to be linked to these radio emissions. When the auroras flare up, the radio signals often spike as well, as if the entire magnetic field is lighting up, broadcasting its energy across space. It's almost like the planet is glowing, not just in the visible spectrum but across all frequencies, with radio waves acting as the invisible whispers of this celestial display. There's something deeply fascinating about Saturn's radio emissions because they remind us that even planets, distant and silent from our perspective, have voices. They communicate through the very forces that govern the universe, through magnetism and electricity, through the dance of particles and waves. Listening to Saturn is like hearing the hidden rhythm of the cosmos, a reminder that everything is interconnected, from the solar wind that blows from the sun to the icy plumes of Enceladus to the vast magnetic field that wraps around the gas giant like an invisible shell. In the end, these strange radio emissions are a testament to the complexity of Saturn's environment. They're a glimpse into a world where forces we barely understand are constantly at play, shaping and reshaping the space around the planet. And while we've learned much about these emissions over the years, their full story is still unfolding as Saturn continues to hum and pulse, its song echoing across the solar system, waiting for someone, somewhere, to truly understand its message. The planet Uranus is a world that defies expectations in so many ways, and its magnetic field is no exception. If you were standing on Uranus, you'd find that the behavior of its magnetic poles would be utterly disorienting, unlike anything on Earth. While we take for granted the idea of magnetic north and south here on our planet, on Uranus, these concepts become almost meaningless. For starters, Uranus is tilted on its side compared to the rest of the solar system, spinning like a barrel rather than a top. This alone creates a surreal environment, but the magnetic field adds another layer of confusion. Most planets have magnetic fields that are roughly aligned with their rotational axes. On Earth, for example, the magnetic North Pole is fairly close to the geographic North Pole, and even though it shifts a little bit each year, the changes are gradual and predictable. Uranus, though, seems to take that rulebook and toss it out. Its magnetic field is tilted by about 60 degrees relative to its rotation, meaning that the magnetic poles aren't anywhere near where you'd expect them to be based on the planet's spin. It's as if the compass needle on Uranus would be completely unreliable for finding anything close to the geographic poles. What's even more perplexing is how dynamic the magnetic field is. On Earth, our magnetic field is relatively stable over short timescales, but on Uranus, it's constantly shifting. Imagine walking in a straight line toward what you thought was the North Magnetic Pole, only to find that the magnetic field around you has started to behave erratically, twisting and turning in ways that make no sense. You'd feel as though you were walking across an invisible landscape, where the landmarks keep shifting without warning. This strange magnetic behavior is thought to be caused by the unique structure of Uranus's interior. Scientists believe that unlike Earth, which has a solid inner core and a liquid outer core that generate its magnetic field through a process called the dynamo effect, Uranus might have a more complex arrangement. The planet's field could be generated by currents within a layer of ionized water or ammonia, sloshing around deep inside its fluid layers. These materials, at extremely high pressures, might not act like regular liquids. Instead, they could conduct electricity in ways that lead to a magnetic field that's offset and twisted. If you were on Uranus trying to study its magnetosphere up close, the experience would be bewildering. The planet's field doesn't just behave differently on the surface, it also fluctuates wildly in space. The magnetic poles seem to wander, influenced by the tilted nature of the planet and the erratic movement of its internal layers. This results in a magnetosphere that's lopsided and highly irregular, sometimes even flickering on and off as Uranus rotates. The way the magnetic field interacts with the solar wind, the stream of charged particles flowing from the sun, would create phenomena that are almost alien in nature, likely leading to strange auroras that could form in places no one would expect, potentially even flickering at odd angles in the sky. For those who've spent their lives studying planets like Earth or Mars, encountering Uranus's magnetosphere would be like trying to navigate a maze without any clear walls. The constant shifts, the unbalanced magnetic field, and the sheer unpredictability of the planet's magnetism might lead to the feeling of being perpetually off balance. Every new measurement or observation might feel as though it defies common sense, leaving researchers grappling to make sense of a world that challenges our most fundamental assumptions about planetary magnetism. Despite its distance and the harshness of its environment, there's something deeply human in the struggle to understand Uranus. The unpredictability of its magnetic poles echoes the challenges we face when reality doesn't line up with expectations. It's a reminder that even in the farthest reaches of the solar system, the universe is more complex than we might have ever imagined, and no matter how much we learn, there will always be phenomena that leave us awestruck and humbled. The study of Uranus's magnetic field is a testament to our relentless curiosity, even when faced with things that seem to defy explanation. Imagine standing on an asteroid, drifting through space in a region that has quietly existed for billions of years, far from the fast-paced activity of planets or the Sun. The Trojan asteroids, caught in the gravitational embrace of Jupiter, are some of the oldest remnants of our solar system's chaotic beginnings. These objects didn't form here, in this stable location, but rather were captured over time, becoming silent witnesses to the story of the early solar system. A story that began long before life on Earth even dreamed of emerging. The Trojan asteroids are found in two distinct groups, one leading ahead of Jupiter in its orbit and another trailing behind, locked into their positions by the balance of gravitational forces between the Sun and Jupiter. This isn't the kind of balance that was planned or predetermined, though. The early solar system was a chaotic and violent place, with planets and smaller bodies colliding, scattering, and constantly changing their paths. At that time, when the solar system was still forming, these asteroids may have originated much farther out, from regions beyond the planets, where icy and rocky bodies roamed freely. The capture of the Trojans into their current positions is a mystery that has intrigued scientists for years. It's believed that these asteroids were not always tied to Jupiter, but were likely scattered objects that wandered through the solar system during a time of great upheaval. As Jupiter formed, its immense gravity began to influence the paths of nearby objects. Some of these objects were flung into the far reaches of space, while others were pulled in closer to the Sun. But the ones that found just the right balance were captured in what are called Lagrange points, regions of stability in Jupiter's orbit where gravitational forces from the Sun and Jupiter cancel each other out. These points, named after the mathematician Joseph Louis Lagrange, act as cosmic parking spots for the asteroids. To understand how these Trojans came to rest in such stable orbits, you have to think about the grand migration of the planets. In the early solar system, it's thought that the giant planets, Jupiter, Saturn, Uranus, and Neptune, didn't form exactly where they are now. They likely shifted positions, moving closer to or farther from the Sun over millions of years. This migration, particularly of Jupiter and Saturn, caused gravitational disruptions that scattered material throughout the solar system. The Trojan asteroids may have been captured during one of these periods, when the gravity of Jupiter and the movement of the planets created a kind of celestial turbulence. If you were there during this period of planetary migration, the skies would have been full of wandering bodies, asteroids, comets, and planetesimals, all moving in different directions as the young planets jockeyed for position. The solar system was still settling down, and in that instability, the Trojans found their place. Some were likely pulled from the region of the Kuiper Belt, a zone of icy bodies beyond Neptune. Others may have formed closer to the Sun, but were pushed outward by the gravitational interactions of the migrating planets. Once captured, these asteroids settled into their orbits around Jupiter, locked into their positions by the planet's gravity. Unlike other asteroids in the asteroid belt between Mars and Jupiter, the Trojans have remained largely undisturbed for billions of years. Their stability has preserved them as time capsules, containing material from the earliest days of the solar system. Studying them is like peering into a museum that has remained untouched, offering insights into the conditions and processes that existed when the planets were just starting to form. If you were to look at the surface of a Trojan asteroid today, you'd see something ancient and untouched by the forces that have shaped the planets. These bodies have likely changed very little since their capture. Covered in dust and pockmarked by the occasional collision, they sit silently in the dark, following their orbits around the Sun. Their origins are tied to a time of chaos and movement, but now they exist in a kind of quiet harmony, eternally bound to the giant planet that holds them in place. In some ways, the story of the Trojan asteroids is a human story too. It's about finding balance in a universe that is often unpredictable and tumultuous. The Trojans, having once been set adrift in the solar system's turbulence, have now found their place, their orbits stable and unchanging. They remind us that in the vastness of space, amidst all the movement and chaos, there are places where things can settle, where equilibrium can be found. Even as the planets continue their endless dance around the Sun, these ancient objects remain in their quiet orbits, as if they've been watching the solar system evolve around them for billions of years and will continue to do so long after we're gone. Picture yourself standing on the surface of Titan, Saturn's largest moon, under a sky that is perpetually cloaked in thick, golden-orange clouds. The air is cold, so cold that water is as hard as rock, and yet the ground beneath your feet isn't made of dust or sand, but hydrocarbons. It feels surreal, almost like stepping onto an alien version of Earth's deserts. But the landscape around you is a vision of strangeness, shaped by chemistry utterly foreign to human experience. Titan is home to vast fields of dunes, but these dunes are not made of silicate grains like those on Earth. They are likely composed of tiny particles of frozen methane, ethane, and other organic molecules that rain down from Titan's thick atmosphere. The dunes on Titan stretch for hundreds of miles across its surface, sculpted into long, parallel ridges by winds that blow through the dense, nitrogen-rich atmosphere. If you were walking through one of these dune fields, you'd see ridges that rise up tens of meters, casting long shadows in the pale light filtering through Titan's haze. The dunes resemble those found in Earth's deserts, like the sand seas of the Sahara or the Namib, yet they are composed of materials that would be liquids or gases under more familiar conditions. This landscape speaks to the peculiar chemistry that dominates Titan's environment, where hydrocarbons exist in abundance, forming complex organic molecules that settle on the surface. The hydrocarbons that make up Titan's dunes are believed to originate from the atmosphere, where sunlight breaks apart methane molecules, setting off a cascade of chemical reactions. Over time, these reactions form heavier organic compounds, like tholins, which slowly drift down to the moon's surface. If you could pick up a handful of material from one of these dunes, it would feel unlike anything on Earth. Not quite sand, not quite ice, but something in between. These particles are thought to be sticky, their tiny grains clumping together due to Titan's low gravity and dense atmosphere, creating dunes that are as much about adhesion as they are about wind patterns. As you stand there, watching the gentle wind reshape the surface, you might realize just how dynamic this world is. Even though Titan is frigid, with temperatures hovering around -290 degrees Fahrenheit, the wind still moves across the surface. It's not a howling wind like those in Earth's deserts, but a slow, persistent breeze that, over time, shifts particles of frozen hydrocarbons into towering dunes. The winds are likely driven by Titan's complex weather systems, which include seasonal changes and even methane rainstorms that occasionally wet the surface. After these rains, the winds dry out the landscape again, picking up loose particles and creating the dunes you see today. Walking across the dune fields would be an eerie experience. There are no familiar sounds. No birds, no rustling of plants, no soft crunch of silicate sand beneath your boots. Instead, the air would be thick, dampened by the heavy atmosphere, making every footstep feel muffled, almost like moving through a dream. The landscape would appear static, yet beneath your feet, the slow processes of erosion and deposition are constantly at work, reshaping the dunes on a timescale too vast for human perception. The existence of hydrocarbon dunes on Titan raises fascinating questions about what it means to have an Earth-like process. Dune formation, happening in an environment so utterly different. Earth's dunes are shaped by silicates, water, and oxygen, all familiar elements in our lives. But on Titan, everything is reimagined. Methane takes the place of water, hydrocarbons substitute for sand. It's as if the same natural forces that act on Earth's deserts, the wind, the settling of particles, the shaping of landscapes, are working on Titan but using entirely different materials. Yet the end result is remarkably similar. A landscape of dunes that looks hauntingly familiar, despite being composed of substances we associate with gasoline or the gas stove back home. As you reflect on the vast stretches of dunes before you, you can't help but think of how alien, yet simultaneously recognizable, Titan's surface is. The hydrocarbons that rain from its sky and form its dunes are the same organic molecules that are central to life's chemistry on Earth. And yet, on Titan, they play a very different role. Not as the building blocks of life, but as the raw material for an otherworldly landscape. This is a place where chemistry and geology intertwine in ways that challenge our understanding of what a planetary surface can be. It's a place that feels distant, strange, yet oddly close to home, reminding us of the shared forces that shape planets and moons across the solar system. Imagine traveling deep into the blue expanse of Neptune, far beyond the swirling storms and violent winds that whip across its atmosphere. As you descend, the visible clouds made of methane ice give way to a hidden world beneath. A world that remains one of the greatest mysteries of our solar system. Neptune's atmosphere is only a thin veil, masking the vast unknowns of its internal structure, which has confounded scientists since the planet was first discovered. If you were able to journey through the layers of this gas giant, what you would find is a place unlike anywhere else, where the familiar rules of physics and materials on Earth break down into something alien. At its core, the true nature of Neptune's interior remains elusive, buried beneath thousands of kilometers of dense gas and high-pressure layers. While we know that Earth's interior consists of a solid core, mantle, and crust, Neptune is a far more complex world, one where the transition between layers is blurred by the sheer pressure and exotic materials that make up its insides. If you stood on a hypothetical platform deep within Neptune, you wouldn't find a clear-cut surface or a rocky core. Instead, you'd encounter a planet where gases become liquids and liquids act like metals, all under pressures unimaginable to us. The planet's outer layers are composed mainly of hydrogen, helium, and methane. But as you move deeper, the gases thicken. Eventually, they are compressed so intensely that they behave more like supercritical fluids, substances that are neither gas nor liquid in the traditional sense. Imagine being immersed in this fluid, a strange, dense substance that defies everything we know about matter on Earth. It's not something you can touch or walk on. It flows, yet it resists pressure like a solid. This part of Neptune's interior is a place where the lines between familiar states of matter blur into something surreal. Deeper still, you'd find yourself in an environment dominated by exotic ices. Though not ices like the frozen water we see in Earth's winters, these are high-pressure ices, likely made of water, ammonia, and methane, all compressed into solid forms by the crushing weight of the planet above. The temperatures here would be blistering, despite being so far from the sun. Under such pressure, materials like water behave in ways we can barely comprehend, forming what scientists suspect to be a superheated, slushy layer surrounding Neptune's core. In this layer, water molecules might be broken apart by intense heat, and free ions of hydrogen and oxygen might circulate like an electrical fluid, generating Neptune's strange and powerful magnetic field. It's thought that this slushy, high-pressure region may be responsible for Neptune's magnetic poles, which are oddly tilted and offset from the planet's rotational axis. If you could somehow keep descending, you'd reach Neptune's mysterious core, the least understood part of the planet. It's believed to be made of a mixture of rock, metal, and ice, but at pressures millions of times greater than anything on Earth, even familiar materials like iron or silicon would be crushed into dense, compact forms we've never seen before. This core might be more like a solid lump of incredibly dense, exotic matter than the molten or rocky cores of Earth or Mars. What makes it even more mysterious is that, despite being far smaller than the rest of the planet, this core may be the reason Neptune emits more heat than it receives from the sun. Somehow, heat is escaping from this distant planet's interior, suggesting that complex, poorly understood processes are happening deep below its visible clouds. Standing on or near Neptune's core would be impossible, not just because of the unimaginable pressures, but also because of the sheer remoteness of the environment. Here, the weight of the planet would crush everything in its path, and the temperatures would rise to levels where the behavior of matter is unlike anything we experience. Yet, it is precisely these conditions that make Neptune so fascinating. A world where the familiar rules break down, and the mysteries deepen with every step you take inward. The secrets of Neptune's internal structure remain tantalizingly out of reach. Even with our most advanced probes and telescopes, we can only infer what lies beneath based on subtle hints, like the planet's magnetic field, heat signature, and gravitational data. To truly understand what's inside Neptune would require a level of exploration and technology that we're still striving to achieve. Yet the pursuit of these answers speaks to a deep human curiosity. The need to understand not just the things we can see, but the things that are hidden, the structures beneath the surface that shape the worlds around us. Neptune's interior is more than just a scientific puzzle. It's a reminder of how much there is still to learn about the cosmos. It challenges our perceptions of what planets can be and how different the conditions of other worlds are from those we know. The complexity of its interior, with layers of unknown materials and phenomena that don't conform to anything we've experienced, is a testament to the diversity of the solar system. It's a place that, despite its distance and inaccessibility, continues to captivate the human imagination, driving us to wonder what other secrets lie hidden in the depths of the planets that share our star. Imagine yourself floating above Jupiter, watching the giant planet as it spins rapidly below you, its banded clouds swirling with violent storms and raging winds. As you gaze toward its poles, something truly extraordinary catches your eye. Bright, glowing lights, shimmering like curtains in the sky. But these aren't the familiar auroras of Earth, tinted with greens and purples. Instead, they pulse with powerful X-ray energy, invisible to the naked eye but detectable by specialized instruments. These X-ray auroras are among the most enigmatic phenomena in the solar system, both beautiful and puzzling, because their source defies easy explanation. Auroras, whether on Earth or Jupiter, are caused by charged particles interacting with a planet's magnetic field, colliding with atoms in the upper atmosphere and releasing light. On Earth, we know this dance is driven largely by solar wind particles, streams of charged particles that blow outward from the sun, following magnetic field lines and creating the familiar northern and southern lights. But Jupiter's auroras are something else entirely, especially when it comes to the X-rays. The most intriguing part is that they don't behave the way we'd expect them to. On Jupiter, these X-ray auroras seem to be pulsing in strange, regular intervals, flashes of X-rays that occur every few minutes. You can picture the planet's poles lighting up in brief bursts, as if some unseen energy is charging and then discharging over and over again. If you could stand on Jupiter, you wouldn't see these flashes directly, but if you had the right sensors, you'd feel the planet's magnetosphere flicker with this powerful energy. The timing of the X-ray emissions suggests a rhythm, almost like the beating of a heart. But where is that rhythm coming from? Scientists have long known that Jupiter's immense magnetic field is far more powerful than Earth's, and it extends far beyond the planet itself, creating an enormous magnetosphere that could engulf several planets the size of Earth. This magnetosphere is constantly interacting with particles, some from the solar wind and others trapped within Jupiter's own magnetic field. But what makes Jupiter's X-ray auroras so perplexing is that they don't seem to be driven primarily by the solar wind, as Earth's auroras are. In fact, they occur even when solar activity is low, hinting that something deep within Jupiter's environment is creating this intense energy. If you were to track the source of these X-ray pulses, you might find yourself drawn to the planet's moons, particularly the volcanic moon Io, which spews charged particles into space. Io's eruptions, throwing sulfur and oxygen ions into Jupiter's magnetosphere, play a role in fueling some of the planet's auroras. Yet even this isn't enough to fully explain the powerful bursts of X-ray energy. It's as if Jupiter itself, with its rapid rotation and dynamic magnetosphere, is generating some kind of internal process that is supercharging these particles, hurling them into the atmosphere with enough force to emit X-rays. There's also the possibility that some unknown interaction between Jupiter's magnetic field and the plasma swirling around it is responsible. Plasma, a superheated, electrically charged gas, fills Jupiter's magnetosphere and could be driving currents that funnel energy toward the poles, igniting the X-ray auroras. But this theory still leaves gaps in our understanding, as the process for converting this energy into pulsing X-rays remains unclear. Standing on one of Jupiter's moons, perhaps on Europa, you might look up at the giant planet in the night sky, knowing that something mysterious is happening in its upper atmosphere. You wouldn't be able to see the X-rays, but the regularity of their pulses would be almost eerie, a constant reminder that Jupiter is far more active and powerful than any of the planets closer to the Sun. The idea that a planet's magnetosphere can behave in such a dynamic and unpredictable way is both fascinating and humbling. It challenges what we know about how magnetic fields work and how planetary systems interact with the particles that surround them. For scientists, unraveling the mystery of Jupiter's X-ray auroras is more than just a technical puzzle. It speaks to our deeper quest to understand the forces that shape the universe. Why does a planet like Jupiter produce such intense, unexplained energy? What is it about this gas giant that makes it so different from anything we know on Earth? These questions push our understanding of physics to its limits, requiring us to think beyond the familiar and consider new possibilities about how planets interact with their environments. In some ways, the search for the cause of these X-ray auroras mirrors the broader human struggle to make sense of the unknown. We are driven to seek answers, even in the face of complexity that seems beyond our grasp. As we continue to study Jupiter, sending spacecraft like Juno to peer deeper into its magnetic field, we come closer to understanding the true nature of this mysterious phenomenon. And yet, there's a sense that even as we solve one puzzle, others will emerge, reminding us that the universe is full of phenomena that challenge and inspire our curiosity. Jupiter's X-ray auroras are a vivid example of how, no matter how much we discover, there will always be more to learn, more questions to ask, and more mysteries waiting to be unraveled. Picture yourself floating in the distant reaches of the solar system, far beyond the familiar inner planets, where the sun is little more than a bright star in a cold, dark sky. Out here, two of the solar system's most enigmatic worlds, Pluto and Neptune, are locked in a cosmic dance that defies our usual understanding of planetary motion. Pluto, once considered the ninth planet, follows a strange, highly elliptical orbit that carries it closer to the sun at times than Neptune. Yet, despite their paths crossing on paper, these two bodies never collide. It's as if they're in a carefully choreographed ballet, moving in harmony without ever touching, bound together by the invisible strings of gravity in a delicate balance known as orbital resonance. This resonance isn't something you'd notice if you were simply watching Pluto and Neptune from afar. But if you could somehow trace their movements over hundreds of years, you'd start to see a pattern emerge, one that reveals just how unusual their relationship is. For every 3 orbits that Neptune completes around the Sun, Pluto completes exactly 2. It's as though Pluto, the smaller and more distant of the two, is being kept in line by Neptune's gravity, pulled into this rhythmic cycle where the two bodies are always in step, even though their distances from each other vary dramatically. If you could watch them over time, you'd see that Pluto's closest approaches to Neptune always occur when Neptune is on the opposite side of the Sun, far away, ensuring that the two never come near enough to interact directly. This kind of orbital resonance is rare and fascinating, because it represents a natural solution to what might otherwise be a chaotic and dangerous situation. Pluto's orbit crosses inside Neptune's, meaning that if their movements weren't synchronized, there could be the potential for catastrophic close encounters or even collisions. But nature, in its complexity, has created this resonance to ensure that never happens. Over millions of years, the gravitational interactions between the two bodies have shaped their orbits into this stable configuration. If you could map out their positions at any point in time, you'd find that Pluto is always just a little ahead or behind Neptune, never directly in its path. Standing on Pluto, if you could somehow survive its frigid temperatures and low gravity, you wouldn't see Neptune in the sky very often. The vast distance between them means that despite their gravitational connection, they're separated by billions of kilometers. Yet the pull of Neptune's gravity is always there, subtly influencing Pluto's orbit, keeping it in line. It's a relationship built on a delicate balance, one that's hard to imagine from our vantage point on Earth, where orbits seem more straightforward and predictable. The story of Pluto and Neptune's orbital resonance is also one of resilience. The resonance has likely existed for billions of years, persisting through the chaotic early history of the solar system when giant planets were migrating and smaller bodies like Pluto were being scattered in every direction. It's thought that Neptune's migration outward from the Sun played a key role in capturing Pluto into this resonant orbit. As Neptune moved, its gravity pulled on Pluto, gradually adjusting its path until the two fell into their current configuration. From that point on, their orbits were locked together, ensuring long-term stability despite the constant gravitational tug-of-war happening on a cosmic scale. This stability is surprising, given how elliptical and eccentric Pluto's orbit is compared to the more circular paths of most other planets. Pluto's orbit takes it far above and below the plane of the solar system, swinging in wide arcs that give it a view of the solar system few other objects have. And yet, no matter how far it strays, the resonance with Neptune ensures that Pluto always comes back to its appointed place, never straying too close, never drifting too far. It's a cosmic safety net, one that has allowed both bodies to coexist in this strange part of the solar system for eons without ever disturbing one another's motion. To understand the resonance between Pluto and Neptune is to glimpse the subtle forces that govern the solar system structure. These forces, gravity, orbital mechanics, and resonance, are invisible but powerful, shaping the paths of planets, dwarf planets, and moons alike. If we could unravel the full complexity of how Pluto and Neptune found themselves in this arrangement, we'd see a story not just of two distant worlds, but of the solar system's early tumult, its shifting dynamics, and the quiet order that eventually emerged from chaos. This resonance is like a thread connecting Pluto and Neptune across space and time, a bond that ensures they move in harmony despite the vastness between them. In many ways, Pluto and Neptune's unusual orbital resonance mirrors the unpredictable balance of relationships in human life. Just as these distant worlds stay in sync without ever truly crossing paths, we too often find ourselves bound to others by unseen forces, influences that guide our movements, our choices, our trajectories. It's a reminder that even in the farthest corners of the solar system, where things might seem random or disordered, there is an underlying structure, a rhythm that keeps everything in place. This harmony, so far from the sun, speaks to the quiet but profound order that underpins the cosmos itself. Imagine standing on a platform hovering high above Uranus, looking down into the vast, pale blue expanse of its atmosphere. The planet below appears eerily calm, almost featureless, a world wrapped in cold silence. But as you peer deeper into the layers of this distant ice giant, you begin to notice something strange. An elusive haze, faint yet present, drifting through the upper atmosphere, cloaking the planet in a veil that adds to its mystery. Unlike the thick, vibrant clouds of Jupiter or Saturn, the haze on Uranus is subtle, almost ghostly, and scientists are still struggling to understand why it's there and what is driving it. Uranus is a strange world by any standard. Its axis is tilted so far that it essentially rolls around the sun on its side, creating extreme seasons that last decades. Yet despite its unusual orientation and the harsh environment, the planet's atmosphere is strikingly quiet. The upper layers are dominated by hydrogen and helium, with a trace of methane, which gives the planet its characteristic blue hue. But lurking within this otherwise simple mix of gases is something that defies easy explanation. A thin haze that absorbs light and gives Uranus its unusually dull, washed-out appearance. The haze itself is made up of tiny particles, likely complex hydrocarbons or other organic molecules, suspended in the upper atmosphere. These particles scatter sunlight in ways that make Uranus appear pale and featureless compared to its more dynamic planetary neighbors. But what's puzzling is why Uranus has this haze at all, and why it seems to differ so much from the other gas giants in the solar system. Neptune, which shares many similarities with Uranus in terms of size, composition, and distance from the Sun, doesn't exhibit the same level of atmospheric haze. Neptune's atmosphere appears more vivid, with visible storms and dynamic weather patterns, while Uranus remains veiled in this strange, unchanging fog. If you could drift down through the layers of Uranus' atmosphere, you'd find that this haze isn't limited to a single altitude. Instead, it permeates much of the upper atmosphere, where temperatures are incredibly cold, cold enough for methane to condense into clouds of ice. But the haze isn't just methane ice. It's something more complex, likely the result of chemical reactions happening high above, triggered by ultraviolet light from the sun breaking down methane molecules. As methane breaks apart, it forms heavier hydrocarbons, like ethane and acetylene, which then clump together into tiny particles that drift through the atmosphere, forming this persistent haze. But the mystery deepens when you consider the planet's lack of obvious internal heat. Unlike other gas giants, which radiate more heat than they receive from the sun, Uranus is curiously cold. There's no clear source of internal heat driving atmospheric activity, which makes the presence of the haze even more puzzling. On planets like Jupiter or Saturn, internal heat fuels turbulent atmospheres, creating storms, clouds, and dynamic weather. On Uranus, however, the atmosphere seems stagnant, and yet the haze persists, as if something unseen is still shaping the planet's upper layers despite the lack of heat. Standing there in the midst of this haze, you might feel a sense of how fragile and fleeting it all is. The particles that make up this haze are incredibly small, suspended in the vast emptiness of Uranus' upper atmosphere, and yet they have a profound effect on how the planet looks and behaves. It's a reminder of how even the most subtle forces can shape entire worlds. Over time, these tiny particles could fall deeper into the atmosphere, only to be replaced by new ones formed through the ongoing chemical reactions. It's a slow, quiet process, happening far from the dramatic storms and winds of other planets, but it's happening nonetheless. One of the most intriguing questions about this haze is why it hasn't dissipated. Without the same internal heat or the dynamic storms that drive mixing in other planetary atmospheres, Uranus should be a world where such a haze would settle out or be destroyed by sunlight. But something is maintaining this delicate balance, allowing the haze to linger, even as the planet rotates slowly beneath the sun's distant light. Perhaps there are faint currents in the atmosphere that are too subtle for us to detect, or perhaps the chemical reactions are more efficient than we understand, replenishing the haze before it has a chance to disappear. Scientists have long debated what role Uranus' strange axial tilt might play in this phenomenon. The planet's seasons are extreme, with one pole pointed directly at the sun for decades at a time, while the other remains in shadow. This odd arrangement means that Uranus' atmosphere experiences long periods of continuous sunlight followed by equally long stretches of darkness. These extreme conditions could be influencing the formation and persistence of the haze, but no one knows for sure. It's possible that the haze behaves differently during different parts of Uranus' long year, subtly changing with the planet's seasons. But our limited observations haven't yet revealed the full picture. As you drift through this strange, quiet world, the haze feels like a metaphor for Uranus itself, a planet that hides more than it reveals, where the answers to its mysteries lie just out of reach, obscured by thin layers of gas and dust. The unexplained haze on Uranus is more than just a curiosity. It's a reminder of how much we still don't know about the planets in our own solar system, especially the ones that exist on the farthest edges, where sunlight is weak and everything seems frozen in time. In the end, the haze on Uranus might be telling us something about the planet's past, its internal processes, or even its future. It's a delicate balance of chemistry and physics that keeps this veil in place, and understanding it could unlock new insights into how planets evolve, how atmospheres behave, and how even the most distant and quiet places in the solar system are shaped by unseen forces. The mystery of Uranus haze remains, waiting for the next mission, the next observation, or the next breakthrough to finally reveal what's hiding beneath that pale blue sky. As you drift through the outer reaches of the solar system, past the gas giants and their familiar moons, you find yourself in the realm of Neptune, the farthest planet from the sun. There's something strange about Neptune that catches your attention. Like the other outer planets, Neptune has a set of large moons, the most famous being Triton, a frozen world captured long ago by the planet's gravity. But as you look closer, you realize that Neptune is missing something. Small moons, the kind that typically swarm around gas giants, scattered like debris in a cosmic ballet. Where are they? Why does Neptune, with its massive gravity, seem so devoid of these tiny companions? At first, this absence might seem insignificant, just a quirk of Neptune's distant location. But the lack of small moons is more than just a curiosity. It's a puzzle that defies the usual patterns we see in the solar system. Jupiter, Saturn, and even Uranus are surrounded by a multitude of small moons, many of them likely captured asteroids or fragments from ancient collisions. These moons, some only a few kilometers across, add to the complexity and richness of their planetary systems, hinting at the chaotic processes that shaped them over billions of years. Neptune, however, doesn't follow this script. Despite being similar in size and mass to Uranus, Neptune has far fewer small moons, and the ones it does have are unusually spaced and scattered. If you could travel closer to Neptune, exploring the space around it, you'd notice that the planet's gravity is more than capable of capturing and holding onto smaller objects. So why are they missing? One possible explanation might lie in the history of Triton, Neptune's largest moon. Triton is an oddity in the solar system, an object that orbits Neptune in the opposite direction of the planet's rotation, a clear sign that it was captured rather than formed in place. Triton is likely a former Kuiper Belt object, a distant icy body that strayed too close to Neptune and was pulled into orbit. But this capture wasn't a peaceful event. Triton's arrival would have been cataclysmic, disturbing the orbits of any other small moons that might have been orbiting Neptune at the time. Picture Triton as an intruder, barreling into Neptune's gravitational field and wreaking havoc. Any small moons that were already there could have been thrown off course, flung into space, or even pulled into Neptune itself by the chaotic gravitational interactions. Triton's presence would have destabilized the entire system, leading to the loss of many smaller bodies that might otherwise have remained in orbit. It's as if Triton swept the neighborhood clean, leaving behind only a few scattered remnants. This violent capture could explain why Neptune has so few small moons compared to its gas giant neighbors. But the story doesn't end there. Even after Triton's capture, Neptune's gravitational influence extends far beyond the planet itself, and over the billions of years that followed, it could have captured new moons from the surrounding debris in the Kuiper Belt. The Kuiper Belt, a vast region of icy bodies beyond Neptune, is teeming with potential moon material, yet Neptune remains largely devoid of smaller companions. Why hasn't the planet captured more objects in the time since Triton's arrival? One theory suggests that Triton's continued presence acts as a sort of gravitational barrier. With its retrograde orbit, Triton might still be disrupting the ability of smaller objects to settle into stable orbits around Neptune. Any potential moon that gets too close to Neptune risks being influenced by Triton's odd orbit, preventing it from finding a stable home. It's also possible that the region around Neptune is simply more dynamic and chaotic than we realize. The outer solar system is a place of subtle but constant interactions, gravitational nudges from distant planets, passing asteroids, and even the occasional rogue object from the far reaches of the Kuiper Belt. Neptune's location on the edge of this region makes it a target for such disruptions, and any small moon that tries to settle into orbit might be quickly destabilized or ejected by these interactions. The outer solar system is a place of delicate balances, and Neptune's position on the border of this cosmic wilderness might make it harder for small moons to survive. From a human perspective, standing on one of Neptune's existing moons, you would look out into space and feel the strange emptiness around you. There are no swarms of tiny moons circling the planet, no signs of the countless small objects that typically accompany a giant planet's gravitational field. This absence would make Neptune feel isolated, as though something vital is missing from its system. You might wonder how many moons were lost in the past, or whether future missions will eventually uncover tiny, hidden companions lurking in the shadows. The lack of small moons around Neptune also highlights how much we still don't know about the outer planets. We've sent spacecraft to fly by Neptune, but no mission has yet orbited the planet long enough to fully map its system or to search for small, faint moons that might be hiding just beyond our reach. There's a good chance that Neptune does have more moons, tiny ones, orbiting farther out or in hard-to-detect locations. Our current understanding of Neptune's moon system is based on limited data, and there's much more to uncover. In the end, Neptune's puzzling lack of small moons serves as a reminder of the complexity and unpredictability of the solar system. It's a place where giant planets capture and lose moons, where gravitational forces shape entire systems in ways we're only beginning to understand. Triton's presence looms large, both literally and figuratively, as a key to this mystery, but the full story of Neptune's moons remains hidden, waiting for the next wave of exploration to reveal what really happened in this distant, cold corner of the cosmos. For now, Neptune spins quietly, its few moons in tow, while the rest of the small bodies that should have been there are lost to time and space, perhaps never to be seen again. Imagine standing on the surface of Callisto, Jupiter's second-largest moon, staring out at the distant gas giant, its turbulent storms swirling silently against the black backdrop of space. The ground beneath you is cold, ancient, and seemingly frozen in time. Callisto is a world of contradictions. It's one of the largest moons in the solar system, nearly as big as Mercury, yet it's oddly quiet, geologically speaking. There are no signs of tectonic activity, no volcanic eruptions, no towering mountain ranges being pushed up by internal forces. Instead, the surface is pockmarked with craters that have accumulated over billions of years, evidence that this moon has been bombarded by space debris for eons, with nothing to reshape or renew it. The lack of tectonic activity is strange for a world of its size, and it raises the question: why does Callisto remain so still while other large moons are geologically active? Callisto's silence is all the more striking when you consider its neighbors. Europa, another of Jupiter's moons, is famous for its icy surface and the possibility of a vast ocean hidden beneath. Europa's surface is young and dynamic, constantly reshaped by the tectonic forces of its ice shell, which cracks and shifts over time. Ganymede, the largest moon in the solar system, also shows signs of tectonic activity, with ridges and grooved terrains that hint at an active past. Even Io, the innermost of Jupiter's large moons, is a volcanic powerhouse, constantly spewing lava as its interior churns under the stress of Jupiter's immense gravitational pull. But Callisto, despite its size and proximity to the same gravitational forces, remains untouched by the same processes. The answer to Callisto's tectonic quiet lies in its unique history and composition. Unlike its more active siblings, Callisto seems to have taken a different path in its development. When Callisto formed, it accreted slowly from the material left over from the formation of Jupiter, growing larger as bits of ice and rock came together. But for reasons that scientists are still trying to fully understand, Callisto never heated up enough to create the internal activity that would drive tectonics or volcanism. Its core didn't differentiate as dramatically as other moons did. meaning that the interior of Callisto never experienced the kind of melting or internal restructuring that leads to tectonic forces. If you could dig deep into Callisto, you'd find a mostly uniform mixture of rock and ice throughout its interior, rather than the layered structure typical of geologically active worlds. There's no molten core to create the heat necessary for tectonic plates to form and move, no internal dynamo generating the magnetic fields we see on other moons like Ganymede. Without this internal heat, Callisto lacks the energy needed to drive tectonic activity. The moon has simply been too cold for too long, and as a result, its surface has remained largely unchanged for billions of years. Part of this can also be traced back to the gravitational relationship between Callisto and Jupiter. While moons like Io, Europa, and Ganymede are caught in what's known as orbital resonance, a gravitational tug-of-war that generates immense tidal forces and internal friction. Callisto is orbiting just outside of this influence. It's far enough away from Jupiter that the planet's gravitational pull doesn't create the same internal stresses that lead to heating and tectonic activity on its neighbors. Callisto sits in a sort of gravitational quiet zone, where it escapes the forces that would otherwise stir its interior and drive geological change. It's as if Callisto has been left on the sidelines, free from the chaotic influences that have shaped the other moons. But this lack of tectonic activity isn't necessarily a bad thing for Callisto. In some ways, it has allowed the moon to preserve its ancient surface, providing a glimpse into what the solar system looked like billions of years ago. The craters that litter Callisto's surface are some of the oldest in the solar system, a record of impacts that go back nearly to the time of the moon's formation. If Callisto had been geologically active, many of these craters would have been erased by tectonic movements or volcanic flows, but instead, they remain as relics of the moon's long and quiet history. Standing on Callisto, you'd be looking at a surface that hasn't changed in over 4 billion years, a frozen landscape that has been untouched by the forces that constantly reshape other worlds. The moon's stillness also has implications for the potential of life. On moons like Europa, the constant movement of the ice shell and the presence of an internal ocean have raised hopes that life might exist in the deep, dark waters beneath the surface. But Callisto, with its lack of tectonic activity and likely absence of a liquid ocean, seems far less promising in that regard. The cold, inactive surface offers little in the way of the energy or chemistry needed to sustain life as we know it. Callisto is a world frozen in time, both geologically and potentially biologically. Yet, despite its quiet nature, Callisto still holds a certain allure. Its ancient surface, its sheer size, and its distant, tranquil orbit around Jupiter make it a place of profound stillness in a solar system often defined by chaos and movement. Callisto represents a kind of planetary calm, a reminder that not all worlds are shaped by violence or constant change. Some, like Callisto, remain frozen in their earliest form, offering us a rare window into the deep past of the solar system. As you stand there, contemplating the silent world around you, it becomes clear that Callisto's lack of tectonic activity is part of its identity. It's a world that chose stillness over dynamism, preservation over transformation. And in that stillness, there is a quiet beauty, a sense of endurance that stretches back to the dawn of the solar system itself. Callisto may be cold and geologically quiet, but in its unchanging nature, it tells a story that is as rich and complex as the more active worlds around it. Imagine standing on the surface of Prometheus, a tiny, irregularly shaped moon, as it races through Saturn's complex system of rings. You're aware that something isn't quite right about the path it follows. There's a certain tension in the way it moves, a restlessness that reflects how Prometheus struggles to maintain its place in the delicate balance of Saturn's moons and rings. The gravitational forces pulling on it from all directions create an unstable, almost chaotic, orbital pattern that's in constant flux. Prometheus, with its lumpy, potato-like shape, isn't like other moons that carve steady, predictable paths around their planets. Instead, it weaves a fragile, changing course, constantly influenced by the complex gravitational dance around Saturn. Prometheus orbits Saturn within the narrow gap between the planet's famous F-ring and the broader rings that surround it. This location alone sets it up for an unstable existence. The F-ring, where Prometheus plays the role of a shepherd moon, is not a neat, well-ordered band of material like the other rings. It's a chaotic swirl of icy particles, strands, and clumps that form and dissolve unpredictably. Prometheus doesn't just passively orbit alongside this ring. It interacts with it, tugging at the particles with its weak gravity and creating waves and kinks in the ring as it moves past. With each orbit, Prometheus pulls some of the material out of place, creating temporary streams of particles that stretch behind it like the wake of a boat. This continuous interaction creates a feedback loop, where the ring influences Prometheus' orbit just as much as the moon shapes the ring. The moon's unstable orbit is further complicated by the presence of Pandora, another small moon that orbits just outside the F-ring. The gravitational tug-of-war between Prometheus and Pandora causes their orbits to shift and change over time in a way that's far from regular. Prometheus is constantly being nudged by Pandora's gravity, which leads to small but significant changes in its orbit, sometimes pulling it slightly closer to Saturn, and other times pushing it further out. This constant shifting means that Prometheus never really settles into a stable orbit. Instead, it oscillates back and forth unpredictably, caught between the gravitational influences of Saturn, Pandora, and the ring material itself. You might feel a sense of unease as you watch Prometheus' path unfold over time. It's as though the moon is always on the edge of losing control, its movements dictated by forces far greater than itself. It never follows the same exact route twice, and over the course of decades and centuries, these tiny shifts could add up to significant changes in its orbit. The moon's erratic path is a testament to the immense complexity of Saturn's ring system, where gravity, collisions, and interactions between countless objects create a web of interrelated motions. Prometheus, with its irregular orbit, is just one piece of this intricate puzzle, but it highlights the fine balance that exists within the system. What's fascinating is that despite its chaotic orbit, Prometheus plays a vital role in shaping the F-ring. Without it, the ring would likely look very different. Prometheus helps to confine the ring particles to a narrow band, preventing them from spreading out into space. But in doing so, it also disturbs the ring's structure, creating gaps, waves, and even clumps of material that appear to drift in and out of view. Prometheus may be small, only about 86 kilometers across, but its gravitational influence has an outsized effect on the ring system, a reminder of how even tiny moons can have profound impacts on their surroundings. If you were to study Prometheus' orbit over many years, you'd notice that it never quite settles down. The constant nudging from Pandora and the gravitational pulls from Saturn and the F-ring particles ensure that Prometheus is always in flux, always slightly out of sync with the forces trying to control it. It's this instability that makes Prometheus so intriguing, a moon that seems unable to find a steady path through the universe. And yet, despite the chaotic forces acting on it, Prometheus continues its role as a shepherd, guiding the F-ring in its uneven, unpredictable journey around Saturn. Standing on Prometheus, you might feel the weight of these invisible forces. The moon's irregular, constantly shifting orbit would give you a sense of how fragile its position is, as though at any moment it could be sent spiraling out of control. But for now, Prometheus remains in its delicate dance, pulled this way and that by the gravitational currents around it. The unpredictability of its orbit is part of what makes this tiny moon so captivating, a reminder of the delicate balances that govern the motions of objects in space. Prometheus' erratic orbit is a glimpse into the chaotic beauty of the solar system, where nothing is truly fixed and everything is in constant motion, shaped by forces both large and small. The moon's tenuous grip on its path around Saturn reflects how even the most stable-seeming objects in the cosmos are subject to change, influenced by the complex web of gravity that binds them together. Prometheus may never find stability, but in its restless orbit, it reveals the hidden dynamics that drive the motions of the universe. Imagine standing on the surface of Venus, if such a feat were possible, looking up at the sun. The sky would be a sickly, sulfuric yellow, and you would notice something disorienting. The sun doesn't race across the sky like it does on Earth, but rather it crawls, dragging its light across the heavens so slowly that you would hardly notice it moving at all. A single day on Venus, the time it takes the planet to make one complete rotation on its axis, lasts longer than an entire Venusian year. To put it in Earth terms, the planet spins so sluggishly that a day on Venus stretches out to about 243 Earth days, while its orbit around the Sun takes only 225 Earth days. In the vast silence of space, Venus seems almost like a prisoner, caught in a hypnotic lethargy, trapped in an eternal, slow-motion dance. It rotates in the opposite direction to most of the planets, including Earth. If you could stand there for that impossible duration of a day, you'd see the sun rise in the west and set in the east. A strange reversal that mirrors Venus' own defiance of conventional cosmic patterns. There's an eerie sense of timelessness about it, as if the planet exists in a different rhythm altogether, refusing to be rushed by the universe's clocks. The outer planets, the gas giants like Jupiter, Saturn, Uranus, and Neptune, spin with an almost furious energy, completing rotations in mere hours. They seem restless, hurrying through their cosmic routines, their vast atmospheres churning in rapid cycles. But Venus remains unhurried, a world caught in its own slow, deliberate cycle. The reasons for this stark contrast in rotational speed are likely tied to the chaotic events that shaped the early solar system. A collision with a protoplanet or some other celestial body, perhaps, might have thrown Venus into its peculiar retrograde spin. Unlike the gas giants, which formed in the more distant, less turbulent regions of the solar system, Venus was born closer to the Sun, where gravitational forces and early impacts would have been far more violent. There's a human element in this, a kind of recognition that despite our best-laid plans and careful structures, the universe operates on its own incomprehensible timeline. Venus is a planetary embodiment of patience, a reminder of how time can stretch and bend in ways that feel almost unbearable to human understanding. The outer planets, with their fast rotations, might mirror the frantic pace of modern life, where hours blur together in rapid succession, filled with motion, noise, and progress. Venus, though, is the planet of waiting, of stillness, of long silences that force reflection. It turns in its own time, acknowledging neither urgency nor haste, as if it has known something all along that the outer planets, and perhaps humanity itself, have yet to realize. As you imagine yourself under that hazy Venusian sky, you might wonder what it would mean to experience time in such a way. To feel the slow crawl of the day, each moment drawn out to a degree almost beyond comprehension. Would you become impatient, trying to speed things up, or would you surrender to the slowness, allowing yourself to fall into the planet's hypnotic rhythm? It's a question that resonates with a deep truth about life itself. The slow rotational speed of Venus doesn't just speak to its physical characteristics, but to something deeper, something more existential. There's a strange beauty in its slowness, an invitation to see time not as something to be mastered, but as something that simply is. Indifferent to our desires, resistant to our control. Venus may be slow, but it is constant. It turns at its own pace, immune to the chaos of the faster, more dynamic outer planets. To observe it is to see a reflection of the parts of human life that we often try to ignore. The long waits, the periods of inertia, the moments when nothing seems to be happening, but in truth, everything is shifting beneath the surface. It forces us to confront our relationship with time, and to ask ourselves whether speed is always the measure of progress. The outer planets may hurtle through their rotations, but in their haste, they might miss something profound that Venus, in its slow turning, holds close. There's something haunting about the moons of Jupiter, silent, distant worlds caught in the pull of a planet that itself exerts a force so immense. It becomes hard to imagine what that interaction truly feels like. If you could stand on one of these moons, Europa, perhaps, with its icy surface stretched out beneath your feet, you might feel like you're in the middle of a conversation, one that takes place not with words, but with forces too vast for human senses to directly perceive. Jupiter's magnetosphere, the largest in the solar system, extends far beyond the planet's physical boundaries, wrapping its moons in an invisible, ever-present grip. Yet, something strange happens in that interaction, a mystery that leaves scientists reaching for answers that seem just beyond their grasp. The relationship between Jupiter and its moons isn't a simple one of orbit and pull, as if the moons are mere objects circling a giant. Instead, it's more dynamic, more charged, as though they are locked in a subtle exchange of energy, an invisible current passing between them. Jupiter's magnetic field is immense, powerful enough to influence not just the planet itself but everything around it, and the moons, particularly Io, Europa, and Ganymede, interact with that field in ways that defy simple explanation. There's an almost eerie synchronicity to it, a strange magnetism that seems to pulse between the giant planet and these far-flung satellites, as though they are in communication on a level we can't quite understand. Take Io, for instance. the most volcanic body in the solar system, a world of fire and fury orbiting within Jupiter's magnetic reach. As Io orbits, it cuts through Jupiter's magnetosphere, creating a kind of electrical interaction, a current, a flow of energy that connects the moon to the gas giant. It's as if a wire is stretched between them, and through it passes an electric charge so vast, so raw, that it creates auroras on Jupiter, lights that ripple and dance at the poles of the planet, distant signs of the unseen forces at work. Yet, why this happens with such intensity on Io, and less so on other moons, remains elusive. The very act of this interaction seems like the unfolding of a cosmic drama, where the reasons are hidden, but the effects are undeniable. Human beings often feel like we are capable of understanding the world through careful study and measurement. But here, on the scale of these colossal magnetic fields, our comprehension falters. We can observe the effects, chart the glowing auroras, measure the electric currents, but the full picture eludes us, like trying to grasp something ethereal. Europa, with its smooth ice shell hiding an ocean beneath, is another player in this magnetic dance, though its role is quieter, more mysterious. Something in Jupiter's magnetosphere stirs beneath the ice of Europa, perhaps subtly altering the flow of its hidden ocean, influencing it in ways we have yet to discover. Ganymede, with its own magnetic field, offers another layer to the enigma. Its field interacting with Jupiter's, creating overlapping zones of influence, a complex magnetic tapestry that remains largely undecoded. Imagine what it would be like to stand on one of these moons, not just feeling gravity pulling you to the surface, but also sensing this invisible force tugging at your very molecules. What would it be like to be caught between such immense powers, to be part of a magnetic interaction that plays out silently, endlessly, in the void? It's a humbling thought to recognize how much we don't know, how these moons, so distant, are players in a magnetic play we only faintly perceive. You might feel small, dwarfed by the scale of these interactions, as if the universe is filled with invisible threads, holding everything together in a web of forces far beyond human comprehension. These magnetic interactions, whether they are sparks of electric energy, as on Io, or the strange, unexplained shifts deep under the icy crust of Europa, serve as reminders that even in the most vast, open stretches of space, forces are at work, unseen but deeply felt. They are beyond our immediate senses, but they have the power to shape entire worlds, to ripple across the solar system, like a distant echo of something far more profound. Jupiter's magnetosphere and its moons interact like dancers moving through the same gravitational field, tethered by invisible forces, yet each with a role and rhythm we can barely begin to map. In many ways, this interaction between Jupiter and its moons mirrors the human desire to understand the unknown. We sense there's something more, something beneath the surface, some deeper structure to the cosmos that we can only just begin to glimpse. Yet, no matter how many instruments we aim at the sky, how many measurements we take, the full answer remains out of reach, tantalizing, pulling us toward it like a distant magnetic field. The unexplained forces between Jupiter and its moons act as a cosmic reminder of how much mystery remains, and how even in the vast emptiness of space, the most profound interactions are often the ones we can't fully see. Imagine drifting close to Neptune, that cold, distant world enveloped in blue hues, its rings faintly visible, like whispers of dust suspended in the vastness. These rings aren't the perfect, symmetrical bands we imagine when we think of Saturn. Neptune's rings are fragmented, uneven, and in some parts, they barely even exist. Instead, there are arcs, clumps of material scattered unevenly along the planet's rings, defying expectations. They cling to specific areas as though held in place by some unseen force, and their very existence challenges the way we understand the behavior of planetary rings. If you were to observe Neptune's rings from a closer vantage, you'd see that these arcs are not like any other ring structure in the solar system. Most rings, like those of Saturn or Uranus, spread out evenly, dispersing particles in a smooth, continuous flow. But Neptune's rings break that rule. The arcs gather in clusters, and their distribution feels chaotic, unbalanced, almost as if something holds them in place against the natural laws that should disperse them evenly. It's like watching a tide that never fully comes in, pieces of it forever stuck in mid-motion. The reason for this unevenness remains shrouded in partial mystery. There's a theory involving the moon Galatea, a small satellite of Neptune, that suggests it may be acting like a shepherd, guiding these arcs and keeping them from spreading out. Galatea, locked in a gravitational dance with the rings, exerts a subtle influence, creating patterns that shouldn't exist. It's as though the moon refuses to let go of the ring material, holding onto it in certain regions, causing the uneven distribution. But still, the full mechanics of how these arcs stay together isn't fully understood. It's almost as if the arcs are caught between forces, teetering on the edge of dispersing, but forever unable to completely spread out. There's something deeply human about the way we approach this problem. We look at the uneven distribution of these ring arcs and expect them to behave logically, to follow the rules that we've come to know through studying other planetary systems. But Neptune's rings resist that understanding. They remain clumped, not because we haven't looked closely enough, but because the forces at play are more complicated than our theories can currently grasp. It's a reminder that even in the heart of scientific progress, there are still mysteries that tug at the edges of our knowledge, reminding us how much more there is to uncover. If you were standing on Neptune itself, watching these faint arcs glinting in the distance, you might feel a deep sense of wonder mixed with frustration. There's an elusive beauty in their unevenness, in the way the arcs don't quite behave as they should. Yet, like so much of the universe, they suggest a deeper logic, a hidden set of rules that we have yet to fully decode. We can see them, we can measure them, but their behavior remains elusive, just out of reach, like trying to grasp a shadow that shifts as soon as you approach it. Neptune's ring arcs force us to rethink what we know about how matter behaves in space. Most planetary rings, formed by dust and ice particles, naturally spread out over time, distributing themselves evenly along their orbits. But these arcs remain clumped, suspended in their uneven patterns, as though they are caught in a gravitational struggle. There's a tension there, an unresolved force that keeps these arcs from dissolving, yet it's a force we can only theorize about, not fully observe. The interaction between Neptune, its rings, and its moon Galatea might hold the key, but even that understanding feels like just the beginning of an answer. You might imagine yourself trying to explain this to someone, a conversation about how the universe often resists the neat, orderly patterns we expect. The ring arcs of Neptune become a metaphor for all the things in life that refuse to fit into predictable molds. They remind us that unevenness, imbalance, and mystery are part of the very fabric of reality. Just as we can't fully explain why these arcs cling to their uneven distributions, there are moments in life that similarly resist explanation, forces that hold things in place when they seem like they should scatter. The beauty of Neptune's ring arcs lies not just in their existence, but in the way they defy explanation. They are a constant reminder of how much we have yet to learn, how the universe holds on to its secrets with a quiet, deliberate grace. These arcs are not broken, nor are they random. They are a puzzle, suspended in the cosmos, waiting for us to look deeper, to ask better questions, to seek the hidden mechanisms behind their formation. Until then, they remain there, clinging to Neptune like delicate strands of mystery, held in place by forces we can sense but not fully understand. Beneath the icy surface of Saturn's moon Dione, there is a secret that the moon keeps close, hidden under layers of frozen crust. A vast ocean that no one ever expected to find. Dione, often overlooked in the shadow of Saturn's more famous moons like Enceladus and Titan, seemed to be just another cold, cratered world. But as scientists peered closer, using the faint clues from the moon's gravitational anomalies and subtle shifts in its orbit, a picture began to emerge. Underneath that stark, lifeless surface might lie an ocean, trapped between the icy shell and a rocky core. It's an idea that makes you pause, because suddenly, what seemed like just another frozen moon is transformed into something mysterious, something alive with possibility. Imagine standing on Dione, on its frozen plains, feeling the crunch of ice under your feet, while knowing that deep below, kilometers down, there might be water. An ocean moving silently, concealed in darkness. There's something almost poetic about it, this idea that beneath the stillness, there is motion, a hidden depth that no one expected. It's like looking at a person who seems composed, still on the surface, but beneath that calm exterior, a world of emotions, thoughts, and memories churns in complexity, waiting to be understood. What's even more intriguing is how we've only come to suspect this ocean's existence through indirect evidence, like whispers of a truth that can't be fully seen, only inferred. Tiny variations in the moon's gravity, combined with the hints from Dion's internal structure, suggest that the icy crust might be floating atop something far more fluid and dynamic. It's not an easy thing to accept that beneath this dead-looking surface, there could be an entire ocean, vast and cold, pressed between the ice above and the rock below. But it's there, or at least something like it, waiting for us to understand. Dion doesn't boast geysers like Enceladus, shooting plumes of water into space, nor does it have the thick, hazy atmosphere of Titan. Its secrets are buried deeper, quieter, and harder to uncover. Yet in many ways, that makes the possibility of a subsurface ocean even more fascinating. It's not showing itself to us. We have to dig for it, to read between the lines of what little we can observe. The ocean beneath Dion's surface might be small compared to those on other moons, but the fact that it exists at all changes the way we see this frozen moon. It suddenly becomes a place of potential for life, potential for understanding more about how moons like it form and evolve. As you imagine this hidden ocean, you might feel a strange kind of connection to Dion. Its frozen surface, seemingly barren and empty, isn't unlike the way we sometimes present ourselves to the world. Calm, controlled, revealing only what's on the surface. Yet beneath that icy shell, there's movement, there's depth, there's complexity. The idea of an ocean on Dion speaks to that very human feeling of hiddenness, of having an interior life that no one else sees, one that exists in parallel to the world we show. What drives this ocean to exist beneath the surface? The gravitational forces exerted by Saturn, the tidal interactions that gently flex and squeeze Dion's core, creating just enough internal friction to keep that water from freezing solid. It's a delicate balance, one that allows this ocean to remain liquid in a place where the surface is frozen hard as rock. There's something fragile and powerful in that balance, a tension between cold and warmth, between stillness and motion. The gravitational pull of Saturn stirs the ocean, even though it remains hidden from sight, shaping Dion in ways we can barely detect from afar. It's a strange thing to think about. A world so far from Earth, so cold and remote, might have something as familiar as water beneath its surface. It makes you wonder, too, what other worlds might be hiding beneath their surfaces, what other oceans might be waiting to be discovered, places where life, in some form, could be thriving in the deep, unseen spaces between rock and ice. Dion's ocean might never erupt into the open the way Enceladus does, but its presence is still profound. It's a reminder that even in the farthest reaches of our solar system, there are secrets waiting, hidden under layers of ice, patiently awaiting the moment when we finally uncover them. In a way, Dion's subsurface ocean forces us to reconsider what we think we know, not just about moons or planets, but about the nature of discovery itself. Sometimes the most remarkable things aren't the ones that announce themselves with dramatic, visible signs. Sometimes they're the ones that stay hidden, revealing their depth only to those who take the time to look more closely, to listen for the quiet clues they leave behind. The ocean beneath Dion is one of those secrets, silent, mysterious, and filled with the potential for discovery, if we only know where to search. There's something unsettling about Saturn's magnetic field. Unlike Earth's, which is slightly tilted but still aligned with the planet's axis of rotation, Saturn's magnetic field is oddly centered, yet not where it should be. It's like encountering someone whose external posture appears perfectly composed, but there's something subtly off beneath the surface, something askew that you can't quite put your finger on. Saturn's magnetic field is almost aligned with the planet's axis. Too aligned, in fact, a precision that doesn't sit comfortably with our understanding of how these fields should work. Yet, even with this near-perfect alignment, the field itself is off-center, pushed slightly away from the planet's core, creating a dissonance between what we expect and what we actually find. Magnetic fields are usually messy, the result of turbulent molten cores generating currents that twist and churn, creating complex, shifting poles. On Earth, this results in a slight tilt, something we've come to understand as normal. But Saturn defies that norm, showing us a field that's eerily straight, almost unnaturally so, as if it refuses to follow the rules. And yet, despite this unnerving symmetry, the field doesn't sit directly at the planet's core. It's offset, skewed just enough to leave scientists questioning what's happening deep inside Saturn. Imagine standing on one of Saturn's moons, looking at the gas giant hanging in the sky, its rings spinning in slow, graceful arcs. You know that somewhere beneath those clouds lies the source of this magnetic field, but it's not where it should be. It's as though the planet is hiding something, or perhaps struggling with an internal tension, like a person who appears outwardly composed but is wrestling with some deeper conflict. The tilt isn't extreme, just a small deviation, but in a system as vast as Saturn, even a small shift becomes significant. It suggests that something is happening inside Saturn that we don't fully understand, some force or process that has pushed the magnetic field out of perfect alignment. What makes this even stranger is that Saturn's field behaves almost as if it were deliberately constructed to be stable, symmetrical, and yet fundamentally off balance. Most planetary magnetic fields, including those of Earth and Jupiter, are generated by the swirling movement of molten metal deep inside, constantly shifting and causing the magnetic poles to wander. But Saturn's field resists that unpredictability. It's locked in place with a symmetry that feels almost unnatural. And still, the core that generates this field isn't perfectly aligned with the planet's center, leaving a gap, a space where something doesn't quite fit. This offset magnetic field makes you think about balance, about how things can seem stable on the surface but carry imbalances underneath, hidden but deeply influential. It's as though Saturn is holding itself together, keeping the field neatly in place, but only by displacing it, keeping it just off-center enough to maintain its strange harmony. It's a tension that feels oddly human, a balance of forces, an appearance of order, but with a hidden imbalance just below the surface, threatening to disrupt that order if nudged too far. The tilt and displacement of Saturn's magnetic field offer a glimpse into the deeper workings of the planet, into forces we can't directly see but can infer through their effects. There's something almost poetic in that. This idea that the magnetic field, something invisible yet immensely powerful, can be both perfectly symmetrical and yet imperfectly placed. It's a reminder that even in the most organized systems, there are imperfections, slight shifts that reveal the complexity and unpredictability of the universe. Scientists suspect that this odd configuration might have something to do with the deep interior of Saturn, where a layer of metallic hydrogen could be generating the field. But the exact reason why the field is so aligned, yet so displaced, remains a mystery. It's as if Saturn itself is keeping a secret, a hidden truth about its interior structure that we've only begun to glimpse. The offset placement suggests that the internal dynamics of Saturn are more complex than we thought, perhaps involving interactions between layers of the planet we can't yet observe. Standing on that moon, looking at Saturn's vast presence, you might feel the weight of those hidden forces, the unseen currents shaping the planet's magnetic field. It's like sensing a tension between what you can see and what you can feel, a recognition that even in the most magnificent and seemingly orderly systems, there is an undercurrent of chaos, of imbalance, lurking just beneath the surface. Saturn's magnetic field, with its strange tilt and off-center alignment, becomes a symbol of that deeper truth, a reflection of how even the most carefully composed structures carry within them the potential for disorder, for shifts and changes we can't always predict or control. In the end, the tilt and displacement of Saturn's magnetic field invite us to look deeper, to question our assumptions about how things should work, and to embrace the complexity of a universe that often resists simple explanations. It's a reminder that balance isn't always about perfection. Sometimes, it's about holding together the imperfect, the off-center, the asymmetrical, and finding beauty in that precarious equilibrium. Enceladus shines with an eerie brilliance, a moon that seems too bright for its place in the cold, outer reaches of Saturn's orbit. Its surface reflects nearly all the sunlight that touches it, an almost unnatural gleam, like polished glass catching a beam of light at just the right angle. It's as though Enceladus has been coated with something pure and untouched, a whiteness that feels ethereal, almost otherworldly, especially when compared to the darker, more rugged moons that surround it. This brightness is no illusion. It's real, and it's strange. Enceladus is covered in ice, but not just any ice. Fresh, pristine ice, constantly replenished by the moon's internal forces. It's this process, the constant renewal of its icy surface, that makes Enceladus so unique. Imagine looking up at this moon from a spacecraft, seeing how the sunlight bounces off it, almost too bright to behold in the otherwise dark expanse of space. You might feel a sense of awe, tinged with something more profound, a realization that this small, icy world is not static, not dead. Beneath its bright shell, something is happening. something that gives this moon its shine. This unusual reflectivity comes from the geysers that erupt from Enceladus's south pole, spewing water vapor, ice particles, and other materials into space. These geysers coat the moon in fresh layers of ice, creating a surface that is constantly renewed, polished by forces from deep within. It's not just a geological oddity. It's a cycle of rebirth, as if the moon itself is washing away any imperfections over and over again, until all that remains is the purest, most reflective surface imaginable. You could think of Enceladus as a kind of cosmic mirror, reflecting not just light, but also the dynamic processes at play beneath its frozen crust. Yet, this brightness also feels like a kind of mask. Beneath the shimmering surface lies a world of hidden depth, a subsurface ocean heated by tidal forces as Saturn's gravity pulls and flexes the moon's interior. This ocean feeds the geysers, which in turn feed the icy surface, creating the perpetual cycle of brightness that makes Enceladus stand out. It's almost as if the moon is putting on a show, presenting a clean, brilliant face to the universe, while beneath, the ocean moves, dark and mysterious, hidden from view. In that sense, Enceladus becomes a metaphor for something deeper, something human, a reminder of how we often project an image of clarity or perfection to the world, while underneath, complexity and unseen forces churn. Enceladus's brightness, its almost blinding reflectivity, feels like an expression of something more than just ice. It's an indication of energy, of activity, of a moon that refuses to fade into the dark, cold void. Other moons may be barren and silent, but Enceladus is alive, in its own way, with geysers that shoot material into space, creating Saturn's earring and coating the moon itself in a glittering frost. If you were to stand on its surface, you would be surrounded by this icy brightness, a surface so pure that it might feel surreal, disconnected from the harsh realities of space. The airless silence would be broken only by the distant hissing of geysers, constantly refreshing the world around you, renewing the light with every eruption. But this relentless brightness, while beautiful, also hides the struggles beneath. The forces that keep Enceladus shining are the same ones that stretch and pull the moon's core, generating heat and pressure in its depths. That hidden ocean, which gives rise to the geysers, isn't just a source of beauty. It's also a sign of the internal battle between cold and heat, between the icy surface and the liquid interior. It's as if the moon's brightness is a shield, a way of containing the powerful, chaotic forces that lie beneath. As you think about Enceladus, you can't help but see parallels with the way we, as humans, often cover up our own complexities with an outward calm or brightness. Just as Enceladus shines brilliantly on the outside while concealing the turbulent ocean beneath, we often present a composed, polished exterior to the world, even when we're struggling with unseen depths. The moon's brightness, then, becomes a kind of metaphor for the way we mask our inner struggles with a surface that looks smooth and untouched. And yet, that brightness wouldn't exist without the hidden forces below. It's a product of the very turmoil that it conceals. In the vast darkness of space, Enceladus stands out not just because it's bright, but because it's alive with energy, with cycles of renewal and rebirth that give it a unique place in the solar system. Its unusual reflectivity, that gleaming surface, is more than just ice. It's the product of a moon that is constantly evolving, constantly refreshing itself in a delicate balance between the forces that seek to freeze it solid and the ones that keep it in motion. It's a world that refuses to stay still, a reminder that even in the coldest, most distant corners of the universe, there are places where life, where energy, where mystery can exist. Enceladus, in all its brightness, reminds us that appearances can be deceiving. What looks serene and pristine on the outside often hides layers of complexity, of movement, of struggle beneath. And just as the moon continues to reflect the sunlight in an almost unnatural way, we too can reflect our own brightness into the world, even when deeper currents pull at us from within. The unusual brilliance of Enceladus, in the end, is not just a physical phenomenon. It's a symbol of the interplay between surface and depth, between the seen and the unseen, between light and the forces that create it. There's something unsettling about the surface of Rhea, Saturn's second-largest moon. It's not the typical, crater-riddled landscape you'd expect from a world that's been drifting through space for billions of years, constantly exposed to the impacts of meteors and cosmic debris. Rhea should bear the scars of that history, its face marked with the countless reminders of collisions and violent impacts. And yet, when you look at Rhea, especially certain regions of it, you're met with an unnerving smoothness, an absence of the deep craters that should be there. It's as if time forgot to leave its mark, or as if the moon has quietly erased part of its own past. Walking on the surface of Rhea, it would be impossible to miss this strangeness. You'd expect to see the same pockmarked terrain that's so familiar across the moons and planets of our solar system, each crater a testament to the chaos of space. But here, in certain places, that chaos seems to have passed Rhea by. It's like meeting someone who carries none of the scars you'd expect from their life, someone whose surface appears almost too clean, too untouched, making you wonder what's hidden beneath, or what forces might have smoothed away the rough edges of their existence. This lack of craters on Rhea is more than just an aesthetic mystery. It challenges our understanding of how moons like it evolve, how they interact with the constant barrage of objects that fly through space. Rhea orbits Saturn in an area that should be filled with debris, and like all other celestial bodies in that region, it should be vulnerable to impacts. So why is its surface so clean in places? What forces could have wiped away the craters, or prevented them from forming in the first place? Some might suggest that Rhea's surface has been resurfaced over time, that perhaps there were once craters, but that they've been covered up by some kind of geological process. But Rhea is a cold, icy world with no sign of volcanic activity, no shifting tectonic plates that could smooth out its features. It doesn't have the dynamic processes that other moons like Europa or Enceladus might use to renew their surfaces. Instead, Rhea is silent, still, and seemingly frozen in place. The smoothness of certain regions, then, becomes even more perplexing, a contradiction that lingers just out of reach, like an answer that's always slipping away. It's tempting to think that something extraordinary must have happened, something that could erase or prevent the formation of craters. Perhaps, in the distant past, Rhea experienced a period of bombardment so intense that it shattered and reformed, leaving behind only a faint memory of that violence. Or maybe, less dramatically, some kind of erosion. Though what form of erosion could act in the vacuum of space remains uncertain, smoothed away the scars. There's a quiet tension in these ideas, because none of them fully explain what we see. It's as if Rhea holds onto its secret, unwilling to reveal why it appears so different from its counterparts. And in a way, Rhea's smoothness reflects something profoundly human, a sense of hidden history, of wounds that have healed too well, leaving little trace of what came before. We all carry the marks of our experiences, but what if, like Rhea, those marks were erased or never fully formed? What would that say about our past, about the forces that shaped us? There's something both unsettling and beautiful in the idea that a surface can seem so untouched, so clean, while carrying beneath it the weight of everything that's happened, or could have happened. Scientists have tried to find answers by studying Rhea's interaction with Saturn's magnetosphere, its icy composition, and the thin atmosphere of oxygen and carbon dioxide that clings faintly to its surface. But none of these things fully account for the lack of craters. It's almost as though Rhea, like a person who survived unimaginable hardship but somehow kept their outer composure, refuses to show the signs of the trauma it's endured. The craters should be there. The impact should have left their mark, and yet they haven't. This absence becomes a question in itself, pulling us deeper into the mystery of what Rhea truly is beneath the frozen exterior. Maybe, just maybe, Rhea's unexplained smoothness speaks to a deeper phenomenon, something we don't yet understand about how moons in this part of the solar system evolve over time. Perhaps it's interacting with Saturn's gravity in ways we can't yet fully perceive. Or maybe there's something in its past, a forgotten event that left it different from what we'd expect. As we look at Rhea, smooth and craterless in places, it's hard not to wonder if we'll ever fully understand what we're seeing, or if some things in the universe are destined to remain unknowable. Standing on Rhea, surrounded by the soft glow of Saturn's rings in the sky, you might feel the weight of that mystery pressing down. It's not the lack of craters that's most striking. It's the questions that absence brings. The surface of Rhea, seemingly untouched in parts, becomes a symbol of something more, a reminder that even in the vastness of space, some things resist explanation. And in that resistance, there's a strange kind of beauty, a stillness that invites contemplation but refuses resolution. As we come to the end of this journey through the mysteries of our outer solar system, I hope you've been as captivated by these strange, distant worlds as I have. From shrinking storms to icy moons that may hold the key to life, each discovery brings us closer to understanding the cosmos. And yet, every answer seems to reveal new questions waiting in the dark. Thank you for joining me in exploring these wonders. If these mysteries sparked your curiosity, don't forget to like this video and subscribe to Quiet Universe. There's so much more to uncover, and the universe always has more to whisper to those who listen. Until next time, stay curious.